Hello and welcome to Sleepy Science. Tonight we'll float through the quiet architecture of quantum reality, where certainty is only a well-behaved probability and possibilities braid into soft interference. You'll ease into the hush where waves keep their poise or gently unravel, wander past paths that add every history at once, listen for what a state really says about you, and learn why some questions can't be asked together without smudging the answer. We'll touch the grain of information that refuses to sharpen, trace the special borders that forbid certain blends, and follow fair games that test locality until the numbers confess. We'll notice how signals stay causal even when correlations feel bold, why non-locality has limits, and how choosing one measurement can guide a distant partner's possibilities without sending a whisper. We'll treat context as fuel for computation, weigh ideas that make outcomes objective, and compare hidden guidance with personal belief and the hard claim that a state is something real. We'll open the toolbox that measures beyond yes-no, meet the most balanced questions you can ask, and read what lies in between without breaking the spell. We'll sample a single system without spending it, rebuild the invisible from many gentle views, and separate plain ignorance from true entanglement. We'll learn the grammar that actions obey, why scale changes stories, how facts shift with the frame you stand in, what rewinding with a mirror and a flip truly preserves, why quantum data won't be fanned out like news, and how to budget the very strangeness that makes all this work. Tell me where in the world you're listening from, your city, your country, and what time it is. And if these slow explorations help you rest, please like, subscribe, and share so other sleepy minds can find their way here. Now take a deep breath, let your shoulders drop, and join me for an unhurried walk along the soft edge where curiosity glows. Wonder does the counting, and the night teaches gently. Why reality is just stable probability. Imagine waking into a world that feels solid, not because it is certain, but because its uncertainties cancel out in reliable ways. The way a crowd's chatter becomes a steady hum from far away, and to your senses, that hum reads as order. Now hold that picture gently while we explore a simple, uncomfortable idea. What you call reality might be the long-term truce that probabilities strike with time, a stability that emerges when countless tiny chances average into predictable patterns you can live inside. You already trust this without noticing it. Flip a fair coin twice and chance is loud. 2 heads, 2 tails, 1 of each. But flip it 1,000 times and the noise quiets down. You expect roughly half heads, half tails. And when the ratio wobbles, you expect it to drift back. Not because the coin remembers, but because the mathematics of large numbers squeezes the wildness into a narrow corridor of outcomes. Your daily life is built on that corridor. Weather forecasters do not know exactly which raindrop will splash your window, yet 5-day rain probabilities let you plan a picnic. Doctors cannot predict the exact moment a single heart cell will fire, yet population-level risk lets them choose treatments. Engineers cannot track each electron in a circuit, yet they design laptops because the swarm behaves consistently. The pattern is the point. And the pattern is stable because chance, when repeated and combined, forms a shape that barely wiggles. In the smallest places, the world is genuinely unsure. An electron chooses a spot on a detector only when measured. Radioactive nuclei decay at random times. Molecular collisions in a gas bounce in ways no mind could list in order. But when you collect many such events, they average into quantities like pressure, current, temperature, and half-life, which hold their values with a loyalty you can count on. You do not see a billion particles, no human does, but you live inside their statistical handshake. And that handshake is what your senses call real. This does not mean reality is pretend. It means reality is layered. At the bottom live possibilities, and above them lives the long-run shape that possibilities carve together. Like a city skyline made of countless bricks. You never memorize the bricks, you memorize the skyline, and the skyline changes only slowly because so many bricks must shift to redraw it. Think about your morning coffee. You cannot name every molecule of water vapor leaving the cup, but you trust the steam to rise, swirl, and fade. Those swirls are probability written in air. They are also reliability written in your routine. Or think about language. You cannot predict your friends' next word. Yet a conversation follows rules that let you understand it. Not certainty, but stable chance. Not a fixed script, but a grammar that narrows what comes next. In the same way, nature uses probability as grammar, and the sentences of the world become readable because the grammar is steady. This is why repeatability matters so much in science. If an effect is real in the sense that it belongs to the stable grammar of the world, then it will show up within the same statistical bounds again and again. If it doesn't, it dissolves into mere noise. Probability does not just describe your ignorance. It also captures the way complex systems settle into habits. Traffic flows find rush hour rhythms. Markets display fat-tailed swings and calm plateaus. Your sleep cycles follow a clock with wiggle room, and even your thoughts show statistical fingerprints. Bursts of focus, drifts of mind wandering that repeat with enough data. The details are different each day, yet the profile is familiar, and that familiarity is what you experience as reality's consistency. You might wonder, if everything is probabilistic underneath, why doesn't my table blur or my keys tunnel out of my pocket? Because the odds for wild outcomes shrink astronomically when you scale up. The same mathematics that lets 1,000 coin flips hover around 50-50 also forces macroscopic weirdness to hide behind absurdly tiny chances. Randomness doesn't disappear. It gets imprisoned by numbers so large they may as well be walls. Another reason is interaction. Systems are never truly isolated. Everything bumps into everything else. Air molecules, photons, vibrations. And those countless interactions constantly test possibilities against their surroundings. The few patterns that survive these tests are the patterns that can coexist with the environment without being instantly scrambled. They are the stable states, the ones the world can hold still long enough for you to notice. Your senses are basically instruments tuned to those survivable patterns. This is also why measurement devices look bulky and boring next to the elegant equations you see in textbooks. An instrument's job is to force a decision by gathering a flood of weak, noisy hints into a strong, stable record. A click on a detector is not one microscopic event. It is a cascade, billions of charges, amplified, filtered, averaged, until the uncertainty at the bottom is converted into a robust mark you can write down. The stability of the record is what lets you do science instead of guessing. In daily life, you perform the same trick more informally. You turn small uncertainties into usable expectations by repeating, comparing, and averaging. You notice that the elevator usually arrives within a minute, that the bread usually toasts in 3, that a friend usually replies within an hour. Usually is not laziness. It is your brain's probability engine summarizing countless micro-events into a model that helps you move through the world with minimal friction. The model is never perfect, but when it is good, your days feel real in the sense that plans mostly work and surprises stay within tolerable bounds. There is a quiet philosophical payoff hiding here. If reality, as you experience it, is the steady shape of many chances, then truth is not a single outcome but a reliable distribution of outcomes. To say, this is how things are becomes, more precisely, this is how things behave on average, when tested fairly and often. That view is humbling because it denies absolute control, and empowering because it teaches you where control actually lives, inside the levers that change probabilities. Wear a seatbelt and you do not guarantee survival. You tilt the odds. Sleep better and you do not guarantee a perfect day. You tilt the odds. Exercise, learn, invest in relationships, and you tilt the odds again. You become a gardener of likelihoods, not a ruler of certainties, and that is enough to change a life. Even identity has a probabilistic flavor. Your preferences are not fixed points, but clusters. Foods you often like, ideas you usually find compelling, habits that recur. Over time, these clusters stabilize into the person you call me, recognizable, because the patterns repeat, not because they never vary. consistency emerges from frequencies. The same is true of groups, cultures, and institutions. Stability is not the absence of chance. It is its containment by repetition, feedback, and memory. If you zoom back to physics, this picture does not require you to accept mystical claims. It simply invites you to see that randomness at the roots and predictability at the branches are not enemies, they are partners. Chance supplies the raw variability, and structure, through large numbers, interactions, and selection, shapes that variability into dependable form. The world is not a rigid clock nor a pure dice roll. It is a clock whose gears are woven from dice, and when enough dice interlock, the hands move on time. The practical test is simple. Can you make successful predictions in the domain you care about, with uncertainty quantified and error measured? And do those predictions hold across repetitions by different people with different tools? When the answer is yes, you have found a stable probability, and with it, a patch of reality worth trusting. So tonight, when the city softens, and you lie there listening to a distant rhythm, the train that passes at almost the same minute, the elevator that hums in familiar intervals, your own breath falling into a pattern. It is not an illusion that soothes you. It is the honest comfort of a world where countless chances gather into a steady glow, and inside that glow, you make your life, not by conquering uncertainty, but by learning its habits and letting them guide you gently toward what matters. Interference patterns, when possibilities collide. Pretend you are standing at the edge of a quiet pond at dusk, and with a playful stubbornness, you toss two pebbles in at once, watching the ripples spread, overlap, and weave a living pattern that seems to appear from nowhere. Now hold that image as a key, because interference is the moment when possibilities overlap, and reality reveals that it is not a single line, but a tapestry, sometimes brighter where the threads align, sometimes missing where they cancel one another to silence. In the lab, we teach this idea with light, because light behaves like the pond's surface in one crucial way. It travels in waves with a rhythm, and when two rhythms meet, their peaks can add or undo each other. Let one lamp shine on a wall, and you get a simple patch of brightness, but split a beam. Steer the halves along slightly different routes, then let them reunite, and a striped design appears. Bright, dark, like a barcode painted by the air itself. What's shocking is that the stripes survive even when the light is so faint that the detector counts single flashes one by one. Each flash lands as a dot, yet over time, the dots build a fringe pattern, as if each photon explored both routes and carried a private metronome telling it where to land more often and where to almost never land. You could say the world is whispering to itself about all the ways an event might occur, and the whisper is the wave, and where the whispers agree, you see a bright line, and where they disagree, you see a dark line where almost nothing shows up at all. If this sounds like fragile, special behavior of light, it isn't. Electrons do it too. Aim a beam of electrons through two narrow openings, and you get the same striped design on a screen, which means matter you can weigh also arrives as a distribution shaped by overlapping possibilities. Push farther, and even clusters of atoms can be coaxed to interfere, and chemists have shown similar patterns with surprisingly large molecules, the kind that rattle when you hold them in your imagination. Interference is not a party trick of physics textbooks. It is a general rule. Whenever a system preserves the delicate timing of its alternatives, those alternatives do not merely sum like ordinary options. They can amplify or erase each other, writing a design that keeps a memory of the paths not taken. You already live with interference every day without naming it. Noise-cancelling headphones feed your ears a carefully crafted opposite sound that meets the unwanted hum and erases it, leaving a sweet hush. A soap bubble glows with shifting rainbow bands because light reflecting from its front and back surfaces travels slightly different distances, so some colors add while others vanish. The faint violet shimmer on your eyeglasses is the ghost of an anti-reflective coating engineered to cancel glare at the wavelengths your eyes mind most. Even your microwave oven reveals interference when food heats unevenly. Hot spots form where waves stand in place and reinforce. Cold spots where they cancel, which is why a rotating plate helps sweep the pattern over the dish. If you want a simple way to picture the math without symbols, imagine each possible path as a tiny arrow that spins like a clock hand as the path grows longer or shorter, where arrows point in the same direction. They add into a long, confident arrow. Where they point against each other, they shrink to almost nothing. That spinning depends on path length, timing, and the medium, so changing distances by even a whisper of a wavelength can flip addition to cancellation or back again. This is the heart of interferometers, the instruments that split a beam, send the halves on a journey, and compare them. With that comparison, we can sense motions so small that no ruler could hope to follow them. Passing vibrations of far off, events nudging space itself, gentle shifts in index of refraction inside a sample, the thickness of a human hair measured with comfort to spare. The machine is not magic. It is a careful listener to harmony and hush. But interference has conditions, and they are as human as they are physical. You only get the pattern when the alternatives are truly alternatives, when the setup does not allow you, even in principle, to tell which way the system went. Give yourself the power to peek, to tag a path with some unmistakable hint, and the pattern fades. It is not that curiosity scares the wave into behaving, but that the world, when marked with distinguishing traces, no longer lets the possibilities overlap cleanly, and the pattern dissolves into a plain sum of separate outcomes. This is why laboratory tables bristle with shields, filters, and extreme quiet. To protect the timing, the phase, the fragile rhythm that lets options remain indistinguishable long enough to interfere. Keep that rhythm intact, and the world reveals. Fine structure, lose it, and you are back to familiar averages. Even the geometry of the setup writes its opinion into the pattern. Narrower openings spread the fringes wider because confining a wave in one place lets it fan out in many directions. Widen the spacing between the openings and the stripes squeeze closer together. Change the color of the light and the spacing changes again, the way a different musical note reshapes a chord. With sound, you can hear this as beating, two near equal notes producing a throbbing, loud, soft that swells in your chest. With water, you can see it as crisscrossing ripples that knit diamonds on the surface. With radio signals, it becomes the frustrating dead zone you find when tall buildings force identical broadcasts to your phone along long and short paths that either help or hurt each other. If you're looking for a moral, it is this. Interference turns either or into both together, then lets the world decide where both becomes more than the sum or less than nothing at all. It is a reminder that outcomes are shaped not only by what can happen, but by how the different ways of happening relate in time. In practical terms, it gives you tools, coatings for lenses, metrology beyond intuition, cancellation of droning, engines, sensors of exquisite sensitivity, and in personal terms it offers a gentle philosophy. Your choices, like waves, are not isolated dots. They interact. Some reinforce the person you want to be. Others cancel progress in ways you only notice later. And learning to keep the useful rhythms aligned. Habits supporting goals, surroundings supporting focus, relationships supporting courage, creates bright fringes in a life that might otherwise look evenly grey. And when you sit quietly after the day's noise and feel a hush drape the room, consider that you are listening to a vast pattern of additions and subtractions. The hush exists because some sounds meet their opposites and vanish, leaving room for the small things to be heard, your breathing, the light scrape of fabric, the mind's inner tide. That too is interference teaching you something. When possibilities collide with care, what remains can be clearer than either possibility. Alone, a pattern not printed on the world, but woven by it, inviting you to notice, to measure, and to wonder. Coherence versus decoherence. The life of a wave. You open a drawer and find two lights. A tiny flashlight that sprays brightness in every direction, and a slim laser that sends a thin, unwavering beam across the room. And in that simple contrast hides the whole story. Coherence is the capacity for many tiny oscillations to keep a shared rhythm over distance and time, while decoherence is how that rhythm frays when the world starts to listen, bump, warm, scatter, and steal the timing, away until all you have left is ordinary shine. To feel what that means, imagine countless microscopic ticks marching in step. Light waves, electron waves, the internal phases of atoms, so aligned that when they overlap, they reinforce one another in a stable way. The way a tuned choir can hold a note so pure it feels carved, and then picture that same choir trying to sing in a busy train station, with footsteps, announcements, and rolling luggage jostling the timing until the harmonies blur into a crowd murmur. The first scene is coherence, the second is decoherence, and the life of a wave is the fragile journey between them. In physics, coherence is not magic, it is bookkeeping. A system remembers the precise relative timing among its possibilities, and because that memory is intact, those possibilities can act together to produce sharply defined effects. Clear interference, ultra-narrow spectral lines, stable patterns that repeat. Decoherence is what happens when the system starts sharing that private timing with its surroundings. Air molecules, thermal radiation, nearby charges, even tiny vibrations in the lab bench, so the timing gets smeared across the environment. Nothing breaks in a violent way. The world simply becomes too informed about which microscopic stories are being told. And once that information leaks out, the different stories no longer cooperate to draw delicate patterns. You have touched the results without naming them. A laser pointer holds its beam because the light quanta inside the device are encouraged to oscillate in step, while a flashlight is incoherent, a million tiny sources each with its own timing. So the beam washes out. A superconductor carries current with no resistance because a vast crowd of paired electrons shares a single macroscopic rhythm, and that rhythm collapses at higher temperature when jostling from the lattice shakes the phase memory apart. In atomic clocks, coherence between two energy states lets time be measured so precisely that we can tell when your altitude changes by a few centimeters, but only because the atoms are cradled in vacuum and cooled close to absolute zero to keep the timing safe. In Bose-Einstein condensates, thousands of atoms behave as one long wave, an orchestra sustained by isolation and cold, so intense that heat itself becomes a rare visitor. If you want a handle that feels concrete without math, think of coherence, length and coherence time as the reach and patience of that shared rhythm. Over what distance and for how long do the oscillations stay in step? Heat shortens both because it boosts random jiggling. Collisions puncture them because they scatter phase like confetti. Stray light and electromagnetic noise tug them off balance the way a passing truck shakes a tightrope. So experimentalists become guardians of rhythm. They pump out air, chill their apparatus, shield it with layers of metal, filter the light, quiet the room, and then, knowing nothing is perfect, they add smarter tricks to fight the fray. One such trick is an echo. Spin a collection of microscopic magnets, let them drift out of sync for a while, then flip them with a pulse so that their errors unwind, and they rephase briefly. This spin echo is not a metaphor, but a real reset button that proves the timing wasn't destroyed, only scrambled in a reversible way. Another trick is dynamical decoupling, a rhythm of control pulses that keeps the environment's nudges averaging to zero, the way you might keep a child's swing centered by tapping at the right moments. And when even that is not enough, we distribute the fragile information across several quantum carriers using error-correcting codes, so that while the environment can nick and scuff a few parts, a careful decoding can restore the intended state, extending the useful coherence far beyond what any single element could sustain. Notice what this teaches you about the everyday world. The reason tables sit still, coffee mugs do not blur, and coins land as heads or tails is not that quantum. Waves are absent at large scales, but that decoherence is ruthless at room temperature and in air. Macroscopic objects are constantly entangled with their surroundings, leaking timing at astronomical rates, so the only states that survive are those pointer states that interactions naturally stabilize, roughly the ones that look like classical positions, and momenta to your senses. The strange superpositions that make interference possible do not explode or violate logic. They simply become untrackable because the environment carries away the phase information into countless degrees of freedom that you neither see nor control. From your point of view, the delicate pattern is gone, and what remains is a robust record, a place where a particle was found, a path a current took, a grain of dust parked at a spot on a windowsill. This shift from private rhythm to public record is not philosophy dressed as physics. You can watch it happen. Increase the pressure in a matter wave experiment, and fringes fade as atoms collide with gas. Warm a superconducting chip, and coherence time plummets as phonons, quantized vibrations of the crystal, wake up and chatter. Let cosmic rays pass through a qubit device, and a single energetic particle can inject enough disorder to ruin milliseconds of careful timing. The antidotes are as down-to-earth as a good refrigerator, thicker shielding, cleaner materials, and smarter control sequences, none of which requires mysticism, all of which require patience. At the frontier, researchers cultivate long-lived coherence in nitrogen vacancy centers in diamond that keep quantum states for milliseconds even at room temperature. In trapped ions held by electric fields, where each ion's sway is quieted so much that a single quantum of motion can be counted. In superconducting circuits cooled to a breath above absolute zero, where the coherence times have grown from microseconds to hundreds of microseconds and beyond, thanks to better fabrication and error correction. And in neutral atom arrays, where thousands of atoms form programmable patterns while lasers choreograph their interactions without letting heat and light tear the timing apart. The race is not just to keep waves alive, but to make them do useful work before the world notices. Computation, secure communication, sensing of unbelievably faint signals. There is a quiet lesson for how you think about collapse hiding. Here, you do not need to imagine a sudden metaphysical snap when an observer looks. It is enough to recognize that information about the alternatives spreads into the environment so fast that from the inside of a warm, busy world, the delicate rhythm becomes unreachable. The interference terms that once mattered become drowned in correlations with air, light, and substrate, and your instruments return single results because they too are heavy participants in that environment, designed to turn whispers into indelible marks. What you call an outcome is the world settling into a state that can resist further jostling. And if you want a human-scale takeaway that stays honest to the physics, take this. Coherence is precious and perishable, so progress, scientific or personal, often depends on creating conditions where the signal can keep its timing longer than the noise can steal it. Sometimes that means literal quiet and cold in a lab. Sometimes it means carving out focused time in a day that otherwise shakes your attention apart. Either way, what emerges from that protected interval is not fantasy, but a clearer pattern. And when you step back into the station of ordinary life, the pattern is sturdy enough to persist. The wave has lived a little longer before it faded, and in that extra life you learned something you could not have learned in the blur. Path integrals, summing every history at once. Picture a night map of a city where your starting pin and destination glow softly, and instead of one highlighted route, the whole screen blooms with every possible way you could walk. Down alleys, across parks, over bridges, even ridiculous loops. And imagine that the city's software doesn't choose a single path, but lets all of them speak at once, each whispering, "Take me," with a tone whose pitch depends on how hard or easy that walk would be. Now keep that map in your mind, because the path integral is physics doing exactly this for a particle. It does not commit to one trajectory. It listens to all of them, adding up tiny complex nudges from every conceivable history. And the pattern of those nudges decides where the particle is likely to be found. In Richard Feynman's picture, a particle moving from here to there is like an explorer with an infinite library of itineraries. Each itinerary carries a tag, a kind of rotating arrow whose angle is set by a quantity called the action, which is a compact bookkeeping of effort over time. how kinetic energy and potential energy trade places along that route. When you sum, the arrows from all routes, directions that differ wildly, cancel like a crowd of voices out of sync, while arrows from paths whose actions change the least, with small tweaks, point nearly the same way and reinforce that quiet selection rule. Small change in action, big survival in the sum, explains why the classical path emerges at human scales, the one that minimizes or, more precisely, makes the action stationary, such as the straight line for uniform motion or a graceful curve in a gravitational field. The classical path is not imposed from above. It is carved out by cancellation. Everything else interferes itself away. This way of seeing motion is more than a clever retelling. It becomes a working engine for predictions wherever the old picture of single trajectories feels cramped. Want to understand a particle crossing a barrier it shouldn't cross? In the path integral, there are histories that go over, histories that skirt the edges, and even histories that linger, each with weights. When the barrier is thin or low, the sum of those rare but non-zero contributions is not zero, so tunneling appears naturally, and you can even estimate how the chance decays as the barrier thickens. Want to see why a magnetic potential you cannot feel can still change an outcome? In a ring-shaped device, two families of roots snake around a field. The potential changes the angles on their tags, shifting how their arrows add, and the tally on a screen moves from bright to dim stripes, without any push being felt along the way. The famous Aharonov-Bohm effect as a phase story written in the language of paths. Even interference through two openings becomes less of a mystery here. You do not think of a particle choosing left or right. You let the sum breathe over the entire canvas, including every zigzag jiggle through either slit and the air between. And the bright and dark design appears because the geometry tunes the relative rotation of contributions. Alter a distance by a whisper, and the tally shifts. If you zoom out from particles to fields, the actual stuff of modern physics, the same idea stretches to fit. A field is a value at every point in space and time, so a history is no longer a line, but a full movie of what that field does, everywhere, and the path integral asks you to add contributions from all such movies. In quantum electrodynamics, this produces the rules that let light and matter exchange quanta. In the theory of the strong force, it becomes a calculator for how quarks and gluons stitch protons together. Because the sum is unimaginably large, we sample it with clever randomness on a grid, a method called Monte Carlo on a lattice, and from those samples, we extract numbers you can compare to experiments, the mass of a proton, for instance. So this isn't poetry, it is a factory floor. The picture also gives you a fresh intuition for why temperature and clutter erase delicate quantum patterns. Each bump from the environment rewrites the tags on the roots, scrambling their relative angles so thoroughly that the reinforcing families lose their edge and the sum washes into something ordinary. The emergence of classical behavior is again an averaging story, but now told through the geometry of actions, rather than loose talk about particles behaving. The lesson is that the world does not switch modes. It filters itself through addition. There are other practical gifts hidden in the framework. By massaging time into a kind that behaves like a fourth spatial direction, the path integral turns quantum problems into cousins of statistical ones, letting tools from one domain solve the other. By nudging the action gently, you can derive response formulas that predict how a system will react to probes, the foundation of much of spectroscopy and materials science. By thinking in paths, you learn to look for saddle points in the landscape of action, special families of histories around which the sum concentrates, and those special families can include instantons, brief, rare events that dominate unlikely processes, the way a single, decisive move can tilt a chess game. If all this sounds impossibly abstract, the travel map image keeps your footing. When the city is smooth and quiet, the best route stands out because all neighboring detours carry tags that rotate quickly and cancel. When the city is rough, many routes contribute comparably, and the destination probability spreads. When you introduce a gentle wind, you twist the tags in a way that favors or disfavors routes depending on how they lean into it. And when you coil the streets around a forbidden courtyard, Some routes still sneak probability across the plaza, but only a little, and less as you widen the courtyard. Everything is in the adding. There is also a personal clarity here that stays honest to the physics. If you accept that outcomes are shaped by the interference of many allowed stories, then what you can control is not a single perfect script, but the weights, the actions that your conditions assign to different stories. In the lab, we cool, isolate, and tune to swing the sum toward coherent families. In life, you adjust context, habits, and incentives so the better trajectories reinforce one another instead of cancelling. Either way, you are not commanding fate, you are curating the contributions. And when you finish this and close your eyes, you can imagine the world's motion not as a thin thread, but as a luminous fog of roots adding and subtracting everywhere at once, and feel a kind of quiet gratitude that from such extravagant possibility, a stable story emerges, one you can measure, predict, and live inside. Because the universe, when asked properly, tells you not just which path is taken, but how the pattern of all paths makes that choice inevitable. What a wave function really encodes about you. Suppose someone handed you a file that claimed to be you, not a photograph, not a diary, but a strange living map that, when consulted correctly, could tell where every tiny part of you might be found, how those parts would likely move next, and which of them are secretly coordinated in ways no photograph could show. That is a fair, everyday picture of a wave function, a compact way of encoding possibilities and relationships. And while it does not narrate your thoughts or your memories, it quietly contains the rules that make your body's matter behave as your body's matter, from the sparkle of salt on your tongue to the elasticity of your skin. The first thing a wave function encodes is a probability landscape, not a single dot, but a textured field of more here, less there. So when you ask where an electron around a carbon atom is, the honest answer is a pattern of likelihood shaped like a lobe or a ring rather than a marble. Chemistry is written in those shapes. Bonds form where two such landscapes fit together like overlapping clouds. And the angle of a molecule in space is the fossil of where those clouds could most comfortably share room. A second thing it encodes is timing between alternatives, not as a clock you can read, but as relative phase. The quiet choreography that decides whether two options help or hinder each other when a process unfolds. Change the phase, and a reaction rate can rise or fall. Light can pass or be trapped. A device can switch from transparent to reflective. That is why a thin film on a lens can calm glare, and why carefully carved layers in a semiconductor can confine light as if it were water in a cup. Third, it encodes who is linked with whom. Entanglement is just a technical way of saying some parts refuse to be described separately, so the wave function carries joint rules for them. If this is found here, that will be found there, not because one reaches across space to push the other, but because the single map already tied their outcomes together. In matter, this linking underlies much of what makes solids solid and insulators insulating, even before you build exotic devices. There is more hidden in the file. Symmetries, for example, the transformations that leave the map unchanged. If turning a system around a certain axis leaves the wave function the same, then angular momentum has a fixed, meaningful value, and that constancy echoes up through everyday life. Why a spinning top resists being tipped, why atoms have tidy spectral lines, why the colors from a gas discharge lamp are a few bright notes rather than a smear. Another subtlety is indistinguishability. Electrons are not labeled marbles, and the wave function reflects that by refusing to change when you imagine swapping two of them in your description. For electrons, this refusal comes with a sign that flips when you swap, and that twist, applied everywhere at once, forbids them from piling into the exact same state, an abstract rule that becomes the Pauli exclusion principle, and then, incredibly, becomes the hardness of matter, the structure of the periodic table, the difference between the graphite that writes in your notebook and the diamond that can scratch glass. If you ask what this has to do with you, the answer is Almost everything physical you recognize about yourself is downstream of these encodings. The way oxygen binds in your blood, the way proteins fold into useful shapes, the way neurons maintain delicate voltages across membranes. These are not random victories. They are permissions granted by wave functions whose forms and symmetries make those events favorable. A wave function also encodes trade-offs in what can be sharp at once. Squeeze its probability too tightly into one place, and the likelihoods for motion spread wide. Let motion be very certain and position smears. This is not a flaw of your instruments, but a structural rule in the map itself, and biology quietly respects it. Ion channels in your brain, for example, exploit quantum-friendly energy landscapes that allow ions to pass swiftly without violating those trade-offs. Photosynthetic complexes shuttle excitations with high efficiency by arranging environments where the wave function's options can find the gentle slopes they need. None of this means mystical thinking controls matter. It means the file's geometry, if well designed by evolution or engineering, channels outcomes. You can recover pieces of your file in the lab by asking many careful questions and collecting answers. Shine light of many colors and record which are absorbed. Nudge with magnetic fields and watch the response. Tap with scanning needles and see how current tunnels across gaps. Each probe is a different translation of what the wave function allows, and together they let scientists reconstruct enough of the pattern to explain and predict. This is why two substances that look similar to the eye can behave utterly differently in electronics or medicine. Their underlying maps are different, their allowed moves and alliances differ, and so their macroscopic habits diverge. Perhaps the strangest fact is that the wave function for more than a few particles is not a picture in ordinary three-dimensional space at all, but a rule in a much larger configuration space, a bookkeeping arena where every coordinate that matters gets a slot. That sounds alien, but it simply reflects the world's complexity. Your body is not a single point, it is a staggeringly detailed arrangement. So the most honest map is one that can speak about many coordinates at once, about how a twist here pairs with a bend there. When simplified correctly, that huge map condenses into effective wave functions for parts, electrons in a material, modes of vibration in a protein, collective excitations in a cell membrane, and those compact maps are already powerful enough to build lasers, design drugs, and explain why a mutation alters function. There are limits to what the file about you contains. It does not list your childhood, it does not encode your favorite song, and it does not whisper the answer to consciousness. What it does, relentlessly, is set the menu of physical behaviors, available to the matter that makes you up, along with the relative ease of each choice. If the menu is generous in one region of possibility space, processes happen quickly and often there. If the menu is stingy, you must supply energy, time, or clever engineering to make things happen. Your body's warmth, the water you drink, the air you breathe, all of these are environments that tilt the menu in specific ways, making some molecular moves routine and others rare. If you want a human translation, try this. The wave function is not your story, but it is your grammar. It does not tell the tale of your day, but it makes some sentences effortless and others tongue twisters. And from that grammar flow the reliable habits you rely on. Bones that support you, enzymes that speed reactions so you can live at room temperature, pigments that catch light so you can see. And if you close your eyes with this in mind, you can feel a quiet respect for the idea that beneath your routines lies a beautifully compressed instruction set, a layered permission slip for matter, whispering not what you must do, but what you can do with surprising ease, and that this whisper, once understood, lets us mend what breaks, design what does not yet exist, and recognize in the most ordinary gestures, the flex of a finger, the spark of a thought, the signature of a map, so rich and so restrained that from it, and from it alone, the familiar you can emerge repeatably in a world that would otherwise be a blur. Complementarity. Why nature forbids total knowledge. Open your hand and imagine you are holding two keys that open two different doors in the same room. One door reveals crisp shapes in perfect focus. The other reveals flowing motion with exquisite clarity. But the room is wired so that only one door can be unlocked at a time, and the moment you choose, the other door becomes unavailable. That is how complementarity asks you to treat nature, not as a single picture that can be sharpened everywhere at once, but as a set of views that must be taken in turns, each view complete on its own terms. And any attempt to demand all at once unravels what you hoped to know. Complementarity is not a poetic excuse for ignorance. It is a rule built into how questions couple to the world. A rule first articulated by Niels Bohr to explain why certain features of a system, like the path an entity takes through space and the fine-grained pattern it can create when allowed to behave like a wave, refuse to be simultaneously uncovered by one and the same experimental arrangement. Choose the apparatus that is sensitive to particle-like tracks, and you gain clear which-way information while the delicate wave pattern vanishes. Choose the apparatus that is sensitive to wave-like superposition, and you see the pattern bloom, while all track-like statements lose meaning. You can feel this in your hand with light and a few cheap tools. Take 3 polarizing filters. Set the first and third at right angles so no light gets through. Then tilt the middle one to a diagonal and watch. To your surprise, some light reappear. You did not overcome darkness by brute force. You altered the question being asked. First you demanded horizontal or vertical. Then you softened the demand to along a slant. And that gentle change opened a route for brightness the original either-or had blocked. The lesson is that incompatible questions do not share a single pool of answers. They carve different answer spaces, and moving between those spaces changes what can be stably said. In electron microscopy, you meet the same law in a different costume. Tune your instrument to reveal the precise positions of atoms, and you sacrifice information about their momenta. Retune it to extract momentum space patterns. The diffraction fingerprints that speak about spacing and periodicity, and the sharp map of positions blurs. These are not engineering accidents, but reflections of a deeper refusal by nature to let certain pairs of properties be sharply true together, because the very act of measuring one fixes the reference frame and timing in a way that erases the conditions needed to define the other with equal conviction. Spectroscopy gives you a time-energy version that you can hear, if not with your ears then with your intuition. A system that emits light for a very long time sings a narrow, pure color. A system that decays quickly belts out a broader note. The width is not instrument sloppiness. It is the unavoidable trade-off between how briefly the process exists and how sharply its energy can be known. Under pressure, collisions shorten lifetimes and lines broaden. In rarefied gas, lifetimes stretch and lines narrow so much we use them to define standards. Once again, you choose which door to open, the how long door or the how precise door, and the world honors your choice by withholding the other. Even in the logic of information, complementarity shows its teeth, and it powers a practical technology. In quantum key distribution, a sender encodes bits in one of 2 incompatible bases, say horizontal, vertical, or diagonal polarizations, and a receiver measures at random in one of the 2. An eavesdropper who tries to learn the key without knowing which basis was used cannot avoid asking the wrong kind of questions some of the time, and those wrong questions leave detectable scars in the data. Security lies not in a wall that cannot be climbed, but in a structure of questions that cannot be answered all at once without damage. Complementarity becomes a shield made of logic. If you want a clean mental model without equations, think of each measurement as a carefully chosen spotlight on a stage. When you angle the beam to freeze the dancer's position, you must narrow the shutter and lock the timing, which drains the lighting that would have highlighted the fluid. Arc of motion. Swing the spotlight to capture the motion sweep, and you must let the shutter run, smearing the exact footfall. Both images are truthful. Neither is the whole performance at once, and the stage refuses to be lit in a way that gives you both truths with equal sharpness in the same instant. Not because of clumsy lighting, but because instant and sweep are different demands on the scene. Bohr's crucial addition, was to insist that this is not about a hidden catalogue of facts that we simply fail to read. For certain pairs of observables, there is no singular fact that satisfies both descriptions simultaneously. No secret file in a drawer labeled exact position and exact momentum together, and the proof lies in the way experiments must be built. An apparatus that can register one property must, by its very functioning, destroy the coherence conditions needed to define the other with comparable precision. The world forces your hand at the level of design, not merely at the level of interpretation. Because complementarity is about the alignment between question and setup, it permeates real devices. Interferometers that sense tiny path length differences lose their extraordinary sensitivity the moment you add a tag that could, even in principle, reveal which arm was used. Single molecule experiments that track a protein's choreography must balance illumination intense enough to see against illumination so intense it perturbs the motion you wish to study. Superconducting qubits can be read out quickly with high confidence or preserved quietly with long memory, and circuit designers spend their days orchestrating pulse shapes and couplings to walk that narrow ridge. In each case, total knowledge remains out of reach, not because of budget or patience, but because the questions grind against each other at the foundations. The temptation is to call this a limitation, but complementarity is also an instruction manual for wiser inquiry. By clarifying which pairs of questions interfere, it teaches you to distribute your curiosity over sequences of measurements, to stitch knowledge from compatible slices rather than to demand a single omniscient shot. Crystallographers pivot between reciprocal space peaks and real space reconstructions. Atomic physicists alternate between trapping and probing. Metrologists use ensembles and feedback to convert a swarm of partial peaks into world-class precision. The rule does not say, do not know. It says no by composing views that can coexist. And that is how modern laboratories reach accuracies that older dreams could not imagine. There is finally a human resonance to carry home without distorting the science. Some aims in your life are complementary in the same structural sense: maximal openness and maximal control, speed and thoroughness, broadcasting and deep listening, and trying to optimize both simultaneously often collapses the very conditions that would let either flourish. The sane move is not to force a contradiction into obedience, but to schedule your doors, to let each door have its hour, and then to integrate the resulting knowledge into a practice that respects what the world will and will not deliver at once. Nature forbids total knowledge in the precise way complementarity states, not as a punishment, but as the price of meaningful questions. Ask well. Accept that sharp answers cast shadows on other questions, and you will discover that the path to understanding is not a single blinding light, but a choreography of lights, each revealing what it alone can reveal, and together composing a picture that is faithful not because it is exhaustive, but because it is honest about what must be chosen and what must be left in the dark. Entropic uncertainty, information's unavoidable blur. Picture yourself trying to read a message written on fog. The letters are real, the message is real, but the vapor refuses to hold sharp edges for long, and no matter how carefully you stare, there's a smear that never yields to focus. Entropic uncertainty is the physics way of saying that this blur is not just in your eyes or in your tools. It's baked into how information is distributed in nature, and there is a precise sense in which some kinds of knowledge cannot be compressed into a single crisp description without the rest of the picture softening around it. Start with a simple guessing game. You're told a secret is chosen from a list, and your task is to ask yes or no questions to uncover it, using as few questions as possible. If the list is balanced and the clues are fair, you can design an efficient strategy, and the fewest questions you need on average is what information theorists call the entropy of the secret, roughly the number of binary answers required to pin it down. Now change the game so that the secret can be revealed in one of two incompatible alphabets, two different dictionaries of clues that don't align cleanly, like trying to identify a song either by its sheet music or by a blurry spectrogram. of its frequencies. Entropic uncertainty says that no matter how cleverly you prepare the secret, if those two alphabets are sufficiently different, the total surprise you must swallow across both descriptions has a fixed, non-zero floor. Trim away uncertainty in one dictionary and it bulges in the other, not because you lack patience, but because the dictionaries themselves refuse to interlock perfectly. In the quantum lab, this shows up when you measure the same system using two incompatible sets of questions. Orient your detector one way and outcomes cluster into a tight distribution. Low entropy, little surprise. Rotate the detector to an incompatible orientation and the distribution must spread. High entropy, lots of surprise. The details depend on how much the two question sets overlap. But crucially, the bound on the combined surprise depends only on that overlap, not on which particular state you chose. This is stronger than the famous trade-offs phrased in terms of sharp numbers like position and momentum. It doesn't just say, you can't nail two values at once. It says, the amount of uncertainty, counted as missing information, has a guaranteed minimum you cannot pay below, which is like being told that no matter how you spin your camera settings, the total grain you face across two incompatible shots is never less than a fixed amount. What makes this profound and practical is that entropy measures the information you are actually missing, not the fuzziness of a single outcome. It is tied to your capacity to compress, predict, and bet. So entropic uncertainty becomes a budgeting rule for knowledge. You can reduce the entropy of one description by investing experimental care, time, or clever state preparation. But the bill comes due elsewhere if your second description is genuinely incompatible. This is why noise reduction, better lenses, colder apparatus, cleaner signals cannot erase certain blurs. Noise is an avoidable sloppiness layered on top, while the entropic bound is a structural flaw below which reality will not cooperate, even in your best-run trials. The cleanest way to feel the difference is with polarized light and a few filters. If you know the light is aligned horizontally, your uncertainty about horizontal-vertical outcomes is near zero, but your uncertainty about diagonal outcomes is maximal. Rotate the preparation to diagonal and the trade flips. Try to be certain of both and the algebra of the filters refuses. Your data, when counted across both bases, stubbornly holds a minimum amount of unpredictability. There are no hidden tweaks that release you from that tax, because the tax is levied by the relationship between the questions, not by your willingness to pay. The same logic powers quantum cryptography. A sender encodes random bits in one of two incompatible encodings, and a receiver measures at random. An eavesdropper forced to guess which basis to use cannot avoid asking the wrong question some of the time. And those wrong questions leave a trail of extra entropy in the observer's data that the legitimate parties can detect. Even if the eavesdropper stores side information in a quantum memory in hopes of fixing mistakes later, a strengthened entropic uncertainty relation still limits how much she can know without raising alarms. The unavoidable blur becomes a shield you can quantify in bits, which is what security needs. Entropic uncertainty also clarifies a subtle philosophical knot. Is your uncertainty about outcomes merely ignorance, or is it an intrinsic feature of the world? The answer here is pleasingly agnostic and operational. Entropy treats both cases on equal footing by focusing on what can be predicted and compressed. If your uncertainty is purely due to ignorance, better prior knowledge will shrink it. If the uncertainty is intrinsic, no prior will help, and the combined lower bound across incompatible questions stays put. Experiments distinguish the two by squeezing every controllable source of ignorance and watching whether the bound persists, and it does. This view connects beautifully to thermodynamics, where entropy also counts missing information, now about the microscopic arrangement of a system's parts. A gas in a box has many micro-configurations compatible with the same pressure and temperature, and our inability to specify which configuration we're in fuels the familiar arrow of time. When you erase a bit on a computer, you are not simply tidying a symbol. You are dumping information into the environment as heat because you've forced many possible microstates into one, and the environment must absorb the difference. That is Landauer's principle in plain clothes, and it hints at why there's a cost to gaining or discarding information. Squeeze uncertainty somewhere and you pay somewhere else, either in thermodynamic currency or in the blur of incompatible descriptions. On the practical side of science, entropic thinking informs how we design sensors, microscopes, and spectrometers. You can push a device toward maximum certainty about one set of features, time resolution say, by shortening pulses and widening bandwidth. But the price shows up as uncertainty in precise color. Aim for breathtaking spectral purity and you lengthen exposures, letting timing uncertainty spread. Engineers turn this into craft, composing instruments and protocols that trade uncertainty between complementary aims in ways that serve the measurement at hand. The entropic bound is the ruler they keep at the back of the drawer, the reminder that certain ambitions will always collide. It also tells us something about randomness we can trust. To generate unpredictable numbers for simulations, lotteries, or cryptography, we can harvest the entropy that incompatible measurements guarantee, then use extractors, algorithms that squeeze messy surprise into nearly perfect uniform bits, to produce randomness that is certified by physics rather than by faith in the honesty of a device vendor. Laboratories now do this by shining light onto beam splitters or reading quantum fluctuations in currents and proving, with entropic bounds, just how many genuine bits of surprise they made per second. If you want a feel for the math without symbols, think of entropy as a measure of how many yes-no questions you cannot skip. Incompatible measurements are two different questionnaires that refuse to share cheap shortcuts. If one questionnaire becomes almost trivial because your state lines up with it, the other becomes stubborn, forcing you to ask nearly every question. There is a threshold on the total number of questions you must ask across the pair. No clever rephrasing gets you below it. And that threshold doesn't care about your preferences, only about how misaligned the questionnaires are. And here is a human-sized lesson that stays faithful to the physics. In your own mind, many goals are informationally incompatible. Trying to deliver a message that is maximally simple and maximally nuanced at once forces a blur no rhetoric can erase. Trying to keep perfect real-time awareness while plumbing deep reflection pushes against the same kind of bound. The wise move is not to curse the blur, but to budget it, to decide where you want crispness and where you can afford grain. Then, to design your day and your devices in ways that honor that budget. Entropic uncertainty is not a failure of knowledge. It is a map of what honest knowledge looks like in a world where questions come with structure. And if you accept that some blur is unavoidable, you gain the freedom to shape it, to push clarity where it matters, to measure and compress what can be measured and compressed, and to stop wasting effort where the world itself says enough. Superselection rules. Forbidden superpositions. Explained. Imagine trying to plan a journey across a continent where some borders are ordinary, slow, bureaucratic, but passable, and other borders are drawn in a special ink that doesn't just stop you from crossing today. It makes the very idea of half in this country, half in that one at the same time meaningless. You can blend cultures, you can stand on a bridge, you can even hold two passports, but there are lines you cannot straddle as a single, coherent traveler, because the rules of citizenship themselves forbid that kind of person from existing. Superselection rules are those special ink borders in physics. They don't merely say, this change is unlikely, or this quantity is conserved. They say, certain superpositions are not physical states at all. And the difference, once you feel it, explains a great deal about why the world looks so classical in some ways, while remaining deeply quantum in others. Start with the friendliest contrast. A conservation law tells you that an allowed process can't alter a quantity, total electric charge, for example. So if you start neutral, you end neutral. But conservation, by itself, does not ban superpositions. You can superpose two different paths in a double slit and still respect energy conservation. You can superpose spin up and spin down and still respect angular momentum. Superselection is stricter. It partitions the space of states into sectors labeled by a quantity that every legitimate measurement must respect, and any phase you try to assign between two different sectors is unobservable. In practice, indistinguishable from a random mixture. So nature treats that attempt not as a fragile state waiting to decohere, but as a non-state, a request the theory won't honor. The cleanest example is electric charge. No apparatus built from ordinary, gauge-respecting matter can reveal a stable relative phase between 1 unit of positive charge and 0 charge. Every observable you are allowed to construct commutes with charge, which means it never couples to an interference term between different charges. So even if you wrote a poem about a half-charged plus half-neutral ion, nothing you could ever measure would distinguish that poem from a classical lottery ticket that's either fully charged or fully neutral. In the border metaphor, charged and neutral live in different countries, and physics refuses to stamp a passport that would let one body be both citizens in a way that could cause interference fringes. There are other, less obvious borders. Fermion, number parity, the evenness or oddness of how many fermionic building blocks you have, is superselected, which is a fancy way of saying you cannot make a coherent both of an odd count of electrons and an even count in a way any allowed measurement could reveal. This univalence rule is a cousin of the spin statistics connection that separates fermions and bosons at a deep level. Parity can also behave as a superselection label in settings where all observables respect the symmetry. By contrast, spin orientation is not superselected. That's why you effortlessly create superpositions of up and down and watch them interfere in real devices every day. So the border there is ordinary, not written in special ink. Why do these forbidden blends appear at all? One honest answer is symmetry. If the only legitimate questions you can ask must honor a symmetry, then the algebra of those questions naturally divides states into blocks that don't talk to each other coherently. The moment you try to write a superposition across blocks, all the cross terms drop out of every physically allowed calculation, as if an invisible customs officer redacted them. Another honest answer is locality and Gauss's law. Changing total charge changes the long-range field that threads all of space, so any phase between different charges would require an impossible global reference to compare against. The supposed phase is not merely delicate, it's undefined. This is different in spirit from decoherence, which you met when we talked about fragile phases leaking into the environment. Decoherence explains how allowed superpositions lose visibility when the world keeps records. Superselection says some superpositions never had visibility to begin with, not because the environment stole it, but because the allowed questions never carried the hooks to grab it. In a lab notebook, decoherence turns a genuine quantum state into an effectively classical mixture over time, whereas a superselected state is indistinguishable from a mixture the instant you write it down, no matter how carefully you isolate your apparatus. Of course, physicists love to probe the edges of any rule, and there is a lively productive tension around whether some superselection rules are absolute or can be lifted if you supply the missing reference frames. For particle number in certain systems, for instance, a big phase reference, like a superconducting condensate or a Bose-Einstein reservoir, can act like a clock that defines what relative phase between different counts should mean, and then interference between components of different number becomes operationally visible in clever experiments. By contrast, for electric charge, the combination of gauge symmetry and long-range fields makes such lifting essentially impossible in ordinary settings, so charge remains a textbook example of a robust superselection sector. The upshot is practical. Some borders are constitutional, others are policy. If you bring the right embassy, a reference device, the policy border can open. If the border is written into the constitution of the theory, it stays shut. These distinctions matter far beyond semantics, because superselection rules shape what kinds of quantum information you can process and how you must build your machines. If operations and measurements must respect a symmetry, they cannot create coherence between sectors on their own. So, coherence relative to a symmetry becomes a resource you must import explicitly. In superconducting circuits, designers keep track of charge offsets and phase references so that what needs to interfere can, while sector labels are guarded because they protect qubits from certain kinds of noise. In atomic and molecular physics, selection rules, practical cousins of superselection constraints, tell you which transitions a light field can actually drive and which remain dark no matter how hard you crank the laser, because the necessary cross-sector matrix elements are simply zero by symmetry. In high-energy physics and condensed matter alike, the notion of distinct sectors underlies why certain excitations never mutate into others without crossing a true boundary. If you prefer a tactile analogy, think of music recorded on separate, lock tracks. The mixing console lets you superpose violins recorded on two mics because they live on compatible tracks. But it will not let you coherently add violins to the control voltage of the power supply. Those signals belong to different layers of the system, and the board is wired to keep them separate. You can play them together as a collage, but you cannot make a single violin note that is simultaneously a precise power supply fluctuation and expect to hear interference. The wiring in physics is the set of observables you are allowed to build, and it simply does not connect certain layers. Notice how this helps your intuition about what the quantum world permits. When you see interference and fragile phase-sensitive behavior, you are watching a performance within a single sector. Fine structure, yes, but on one side of a real border. When you see stubborn classicality that no amount of careful isolation seems able to budge, no fringes between charged and neutral, no clever probe that exposes a phase between odd and even fermion number, you are seeing the map itself telling you the neighborhood boundaries. And when an experiment seems to break a supposed superselection rule, the cleverness almost always lies in smuggling in a reference frame that wasn't previously allowed, not in tearing out the pages of the map. The philosophical moral is gentler than the language sounds. Superselection rules are not scolds, they are cartographers. They draw the partitions that make questions meaningful and predictions stable, and by respecting those partitions, you stop wasting effort on states the world will never acknowledge. You redirect that effort into building the right references, choosing the right sectors, and asking the right families of questions, and the reward is immediate. Cleaner interference, where it's allowed, truer no-goes where it isn't, and devices that work because their ambitions match the wiring of reality. When you lie back at the end of the day, you can imagine the universe as a grand hall with many galleries, some with open archways, where music from one spills into another, some with thick walls where no chord can cross, and your craft, scientific and personal, is to learn which doors swing, which do not, and how to make something beautiful by composing within the rooms that truly connect. Bell Inequalities. Testing. Local reality to destruction. Imagine two sealed boxes placed miles apart, each with two buttons on the front and a single light that flashes red or green when you press. You and a friend agree to press buttons at random, times of your choosing, and every time you later compare notes, you find a haunting pattern. The colors correlate more strongly than any scheme of hidden instructions the boxes could have carried from the start would allow, and yet no signal seems to pass between them while you play. This is the feel of Bell's test, a clean, almost childlike game that asks whether reality can be both local and realistic, and then watches the numbers say no. The core idea is simple but ruthless. If each box carried a private script telling it how to respond to either button, and if your button choice here cannot influence the distant box quickly enough to matter, then there is a hard numeric ceiling on how often your outcomes can line up across all combinations of button choices. That ceiling can be written as an inequality, an upper limit on a score you compute from your joint results. And any world built from local hidden scripts must keep the score at or below that line. Quantum mechanics predicts and experiments see scores beyond that limit, not by a hair but by a clean margin, which means at least one of the comfortable ideas, locality or preset realism, must give way. To make this physical, replace boxes with entangled pairs. Photons whose polarizations or electrons whose spins are born together in a way that ties their results without fixing them in advance. And replace buttons with analyzer settings, such as the angles of polarizers you and your friend choose on the fly. The magic is not in any single run, it's in the statistics over many runs, where certain combinations of settings produce correlations too strong for any shared instruction set to mimic. Think of it like two coins that, when flipped far apart, land heads or tails unpredictably, but in a pattern that beats any conspiracy you could have encoded ahead of time without allowing the coins to chat after the toss, because great claims demand great care. Physicists spent decades tightening the test to shut every reasonable escape route. The locality loophole says perhaps a hidden influence slipped between the labs, so experiments arrange the measurements so far apart and so quickly that the choices and flashes are separated by space-like gaps. No light-speed signal could connect them in time. The detection loophole says perhaps you only counted the friendliest events, so newer detectors catch and keep almost all pairs, leaving little room for biased sampling. The freedom of choice worry says maybe your settings were somehow subtly correlated with the hidden variables at the source, so researchers drive the setting choices with high-speed random number generators, even with starlight from distant galaxies to lean on cosmic randomness. Each refinement answers, "We thought of that," and the violations persist. What falls is not causality. No one sees a message sent faster than light, and changing settings here does not let you steer the distant outcomes to spell words. But the comforting picture that distant things must carry sufficient private facts to explain their joint behavior without any non-local bookkeeping. The results are consistent with a world where the joint answers exist only in the correlations, and we're trying to force a story of separate, pre-existing values that merely line up later hits the inequality wall. The practical consequences are not just philosophical. You can turn bell-type correlations into tools. In device-independent cryptography, for instance, you and a partner treat your detectors as untrusted black boxes and certify a secret key, purely from the strength of the observed violation. If the score beats the local realist ceiling by enough, then an eavesdropper cannot know your bits without spoiling the statistics. Similarly, you can certify genuine randomness. A score above the bound guarantees that no hidden script, however clever, pre-wrote the outcomes, so randomness extractors can distill nearly perfect, unpredictable bits from the raw data with proofs attached. Metrologists are also learning to push sensors past classical limits by entangling their components and reading correlations that classical scripts cannot emulate. If you want a picture that avoids equations and stays honest, imagine trying to explain the game using only envelopes stuffed with instructions. If button A is pressed, flash red. If button B is pressed, flash green, and so on. No matter how you pack the envelopes, if the two players pick A or B independently, and at random, the long-run score has a maximum. Open enough envelopes and that ceiling shows up. Entanglement is like discovering that the envelopes can be correlated in a deeper way than shared ink, in a way that lets the pair behave as a whole even when opened far apart, and the score climbs beyond that classical ceiling while each single envelope still looks fair. The ceiling is not a suggestion, it's a theorem, and the climb beyond it is not a fluke, it's a signature. You might worry this demands spooky whispers across space, but the data guard causality jealously. Your individual stream of reds and greens remains random no matter which button your partner presses, so you cannot send a message with it. Only when you later compare logs do the two strong correlations emerge, as if a story that cannot be told locally reveals itself only in the ledger kept by both sides together. The world, it seems, cares about the ledger. The cleanest way to hold the lesson is to separate what the experiments do from what they do not. They do not show faster than light communication. They do show that any model that insists outcomes were fixed all along by local properties is incompatible with observed correlations. They do not force one unique interpretation of quantum theory. They do force you to abandon the idea that strong correlations must come from shared hidden scripts plus local updates. In exchange, they offer a more relational way to think, where what is predictable and real can belong to pairs and networks rather than to isolated parts. And there is a quiet emotional payoff in accepting this. Your intuition that the world's deepest rules should reward simple, local stories turns out to be only half true. The other half is that some truths live only in the ties, and when you test those ties to destruction, they endure, and in their endurance they give you new technologies, sharper questions, and a gentler humility about what separate and together really mean at the foundations of nature. Kochen Specker. Context rules, not hidden values. Pick up a set of 9 wooden tiles, each stamped with a simple arrow or cross, and imagine a game where you must lay them out in a 3x3 grid so that every row satisfies one rule and every column satisfies another. The rules seem harmless. Count how many tiles in a line point even or odd and make the totals fit. But after a few minutes of rearranging, you feel an odd pressure build. No matter how cleverly you shuffle, the last tile refuses to cooperate, as if the grid itself were booby-trapped against consistency. This is the mood of the Kochen Specker result, which says that for a single quantum system of sufficient richness, you cannot assign pre-existing, context-independent values to all the properties you could measure and still satisfy the logical relations those properties obey when measured together. What comes out of the apparatus depends on the context of compatible questions you ask alongside it, not on a hidden catalogue of answers carried in the system all along. To feel the difference between hidden values and context rules, imagine painting every possible yes or no question you might ask of a system. Every direction a spin might be tested, every orientation of a polarization, either blue for yes or red for no, with 2 constraints. First, when a set of questions can be asked together without disturbing one another, your colors must respect the relation those questions share. Second, your color choice for any single question must not depend on which other questions you choose to accompany it. Non-contextuality, the classical hunch that facts are facts, no matter the company they keep. The Kochen-Specker theorem shows you cannot complete this coloring for a space of dimension 3 or higher. Try to paint the sphere of directions and the rules that look innocent, in isolation, collide when you trace them around the sphere, forcing you into contradictions. Some triads demand a blue here, others demand a red there. And by the time you come full circle, the same direction is required to be both at once. If you want a more down-to-earth version, there is a magic square parody of the logic. You place 9 quantum tests in a square so that the tests in each row can be performed together and must multiply to a certain sign, and likewise for each column, with a final twist that the rows and columns ask for an odd-even pattern that cannot be satisfied by any fixed assignment of outcomes. Quantumly, the pattern is satisfied because the outcomes are not fixed in the old way. They crystallize within each compatible set, and what looks impossible to a non-contextual script becomes routine when values are allowed to be about the joint question, not about solitary labels. This is not the same drama as Bell's theorem, which used separated pairs to show that local hidden scripts fail. Kochen Specker lives under one roof: a single quadrit, a single neutron spin. A single trapped ions levels are enough to force the issue. No messages need be ruled out. No distance games are played. And yet the dream of pre-carved truth for all questions at once still cannot survive. Quantum mechanics permits joint questions to carry structure. Some rules, product rules, that a global, context-blind assignment cannot satisfy, and the failure is logical rather than statistical. On the lab bench, this has been tested not by trying to look inside a system for secret numbers, there are no such numbers, but by checking families of compatible measurements whose outcomes must obey certain parities, and seeing that any non-contextual model would cap a score you compute from those outcomes. The real devices, single photons with paths and polarizations, ions with internal states driven by lasers, neutrons in interferometers, routinely beat that cap even when you vary states widely, confirming that the contextual twist is not a rare accident, but a state-independent feature of the rules. And because these tests work with one system at a time, they close off the escape route that blames stronger than classical correlations on distant coordination. Why does context matter so much? Because the questions that can be asked together carve a shared stage on which answers must agree with one another's algebra. When you tilt the stage, choose a different compatible set, you change the relations the answers must satisfy, and the theory refuses to supply a single list that will work across all stages at once. This is not sloppiness, it is the price of demanding that measurement outcomes reflect the symmetries and constraints of the particular arrangement. A component's value is not like a color painted on a block that you merely reveal. It is more like a role in a play that only exists within an ensemble, constrained by the script that ensemble performs. The consequences reach beyond philosophy, into technology. Contextuality has been identified as a resource for quantum computation, a difference maker that lets certain gate sets escape classical simulation. When you feed a processor special magic ingredients, you are importing precisely the sort of context-sensitive structure that no non-contextual model can mimic efficiently, and speed-ups ride on that import. Error-correcting codes, too, must respect the contextual web. What you can measure simultaneously without wrecking the code's promises depends on which checks are compatible, and designing good codes is partly the art of steering context to reveal the right syndromes while hiding the fragile content. Even at the level of measurement design, context rules tell you how to extract information without contradiction. If you insist on building a sensor that treats outcomes as fixed across all settings, you will chase ghosts in your calibration, because the same element probed in different compatible triads will produce patterns that no single true value can fit. Build with context in mind, calibrate in the joints rather than in the parts, and the ghosts vanish into honest, reproducible behavior. There is also a subtle point about randomness that the theorem clarifies. The unpredictability you see in quantum outcomes is not only a shrug of ignorance, it is bound up with the impossibility of assigning a global truth table that respects all the algebraic ties among compatible tests. Randomness here is partly a symptom of the world refusing to be summarized by a non-contextual script. And yet this is not a license for anything goes relativism. Within each context, outcomes are tightly ordered, obeying relationships so rigid that you can certify devices, generate keys for cryptography, and witness violations of non-contextual bounds with the confidence of a good accountant. The wildness is not inside the context. It is in the impossibility of gluing all contexts together without seams. If you want a tactile image to carry away, think of a map book whose pages overlap slightly, but cannot be bound into a single, perfectly consistent chart. Every page is internally accurate, and any two adjacent pages agree on their overlap, but try to iron the whole world onto one sheet without distortion and the paper buckles. Kochen Specker proves that quantum questions live on just such a manifold of pages, and what we call context are the neighborhoods where questions commute and answers can be assigned coherently. Step across a seam and the old assignments cannot follow unchanged without violating the stitching. Accepting this brings a calm, useful humility to your picture of reality. Not all truth is global, some truth is patchwise, and our task in both science and life is to choose our patches wisely and to record how they meet. When you do, the world stops looking like a tangle of paradoxes and starts looking like a well-made atlas. Local charts that work, global transitions that matter, and a deep lesson that intellect can live by. Facts do not float alone. They take their meaning from the questions that frame them, and learning to frame questions so their answers can stand together is as much part of understanding as the answers themselves. No signaling. Non-local yet causality-safe correlations. Picture two players seated in separate stadiums under different skies, each with a black box that spits out a simple answer, say left or right, whenever they choose one of two, dials and press a button. And imagine that later, when their scorekeepers compare notebooks, the answers line up in a way so precise, it looks like a secret handshake choreographed across the world. Now focus on the twist that matters most. While the eventual comparison reveals a pattern no ordinary shared plan could have produced, neither player can use the box to send a message to the other in the moment. However they wiggle their dial, the other player's local stream of answers stays stubbornly unbiased, as if the box were deaf to distant choices. This is the no signaling principle in plain clothes. The rule that says nature may allow correlations that feel non-local but refuses to let those correlations carry controllable information faster than light, keeping causality safe even while our intuitions wobble. To see why this isn't a lawyer's trick, imagine what signaling would require. If you could influence your partner's immediate statistics by switching your dial, making left show up more often for them when you choose one setting, more right when you choose another, then you'd have built a faster-than-light telegraph. Agree on a code. Dial position for you means 0 or 1. Read the bias on their side, and you're chatting across space without delay. But real entangled systems do not oblige. Your partner's local histogram is locked, typically 50-50, no matter what you choose. The only thing that changes when you turn your dial is how your answers and theirs are correlated. And that change is invisible to either of you alone. It appears only later, when a slow, ordinary exchange of results lets the joint pattern emerge. A familiar everyday analogy helps. Think of a one-time pad in cryptography, where two parties share identical strings of random bits. Each party's bits look perfectly random by themselves. But when the two datasets are combined with the right rule, a hidden message is revealed. Crucially, the sender cannot communicate without actually transmitting their ciphertext, shared. Randomness alone never moves information. The pad merely enables a later decoding. Entanglement is a stranger cousin of that story. The shared resource is not classical randomness, but quantum correlation. And although the joint pattern can beat any classical design, the ban remains. The resource alone does not transmit a message. You must still compare notes through ordinary channels before meaning appears. If you want a physics-flavored intuition without equations, picture each local box as a machine that takes your dial setting and consults a private roulette whose slices are fixed in size, independent of what happens far away. Your action may rewire how your roulette aligns with your partner's, but it never reshapes their wheel in isolation. In technical language, people talk about your partner's marginal distribution being invariant under your setting. In human language, their local stream stays fair. The world permits spooky harmony in the ledger that combines both sides, but it forbids remote control over the other party's solo soundtrack. This restraint is not bolted on after the fact. It's woven into the architecture of quantum evolution. When you poke your system locally, you stir the joint state in a way that, from the other side's perspective, averages out to the same mixed description they started with. All the fancy terms for this, trace over the environment, completely positive maps, are just bookkeeping for a simple outcome. Nothing you do in your lab can conjure a detectable change in the other lab's solo statistics unless a light speed or slower signal also goes out. The update that textbooks call collapse is a change in your knowledge and in the joint correlations, not a shove on the far system's local meter. The principle isn't merely negative, thou shalt not signal. It's a positive design rule that keeps the universe self-consistent across different viewpoints. In relativity, two observers moving differently can disagree on which event happened first when those events are far enough apart. If a measurement here could cause a change there in a way that shows up locally, different observers would disagree about who caused whom, an absurdity. By making the local data invariant and hiding the correlation structure until logs are compared, nature lets every observer tell the same causal story. No usable influence outruns light, and orderings that swap across perspectives never make anyone's equipment contradict itself. You can feel the power and limits of no signaling in famous protocols that ride on entanglement, but refuse to cheat. Quantum teleportation sounds like magic, reconstructing an unknown state at a distance. But it requires the sender to transmit two ordinary bits. Without those bits, the receiver's state is useless noise. When the bits finally arrive at light speed or slower, the receiver applies a fix and the state snaps into place. The correlation was ready, the instruction was not, and the speed limit held. Superdense coding flips the script. By sending one well-prepared particle through a regular channel and exploiting shared entanglement, the sender packs 2 bits worth of distinguishable patterns into that single traveler. But again, a physical transmission happens and light speed rules apply. In both cases, entanglement is a booster, not a smuggler. If you push the thought experiment further and imagine even stronger than quantum nonlocal boxes, hypothetical devices that saturate the allowed correlations while still obeying no signaling, you get a wild lesson. such boxes would not break. Causality either. But they would trivialize many communication tasks, turning hard problems into easy ones by letting partners compute with tiny or zero messages once they meet to compare notes. Our universe declines that extreme generosity, living within bounds that balance power with sanity, but the deeper point survives. Even non-locality, when properly fenced by no signaling, need not menace cause and effect. There is a quieter guardrail paired with no signaling that keeps mischief in check. Monogamy of entanglement, the rule that you cannot share the strongest possible quantum ties widely. If two parties share correlations so tight that they push the tops of the allowed scores, a third party cannot be equally entangled with them at the same time. In practice, this means that if your data with a partner display very strong, clean quantum correlations, an eavesdropper's potential knowledge is sharply limited. Once again, the world channels strength into consistency rather than into loopholes for instant messaging. On the bench, engineers designing quantum networks treat no signaling as a budgeting tool. If node A's setting cannot bias node B's solo outcomes, then any protocol that claims real-time steering at a distance without a regular link is either reporting a calibration artifact or folding in a hidden classical path. The fixes are prosaic: better shielding, faster random setting choices, stricter time tagging, but the diagnostic is principled. Look for local drift as a function of remote choices. If you find it, you found a leak, not new physics. Philosophically, no signaling invites a gentler way of thinking about influence. Not every relationship is a channel. Some ties are reservoirs of potential meaning that only become visible when experiences are shared. You cannot make another mind think a thought by willing it from afar, but you can build common structure, shared keys, shared contexts that let later comparisons produce understanding effortlessly. In the same way, quantum correlations do not let you bark orders across space. They set the stage so that when notes are finally compared, a pattern jumps out that no local story could have choreographed. Causality is honored, and yet the world whispers that separateness is sometimes a surface feature, that what is real can live in the ties themselves. As a practical takeaway, carry this in your pocket. When you hear claims of instant signaling by using entanglement, ask the only question that matters: does the receiver's distribution change in a way they can read without later contact? If not, the claim is a misunderstanding. If yes, the claim contradicts a mountain of mutually reinforcing evidence and would upend both quantum theory and relativity at once. In the long run, no signaling is not a bug that blocks science. It is the very rule that makes clean experiments, secure protocols, and consistent narratives possible. It keeps the universe from tying itself in causal knots while still letting it surprise you with correlations that feel like a conspiracy until you accept the deeper moral. Some connectivities are about structure, not messages, and learning to tell the difference is part of becoming fluent in how the world truly speaks. Cyrelson's bound: why non-locality has limits. Picture a televised game that seems designed to reward clever conspiracy. Two players are locked in separate soundproof rooms and asked random yes or no questions. They can't talk once the game starts, but they can agree on a strategy beforehand, and the prize goes to teams whose answers match in a particular pattern more often than chance. You might guess there's no hard limit. Either the team is ordinary and stays around the classical ceiling, or they cheat with some instant signal and blow the score sky high. But our universe draws a sharper, more intriguing line. If the players share quantum entanglement, they can beat every classical plan, yet can never push their score beyond a precise ceiling called Cyrelson's bound, a just-so maximum that sits strictly below the wild numbers that would be allowed. If nature permitted the strongest imaginable non-local correlations, non-locality is real, but it is measured, not limitless. What sets that ceiling? The short answer is geometry. Quantum measurements are like asking questions along directions in a curved information space, and the correlations you can extract are controlled by angles between those directions. You and your distant partner can tilt your detectors to make some answer. Pairs agree more often, and you should. Yet the same tilts that help one pairing necessarily spoil another, because the questions do not all live on a flat chessboard. The inner products between the underlying vectors demand trade-offs, and when you add the four correlations that define the classic Bell game score, the geometry clamps the total. No amount of cleverness with entangled states or fancy measurement gadgets lets you exceed that geometric limit. In a laboratory language, the operators that represent your yes-no questions cannot all be aligned to please every pairing at once, and the algebra refuses to multiply into a number higher than Cyrelson's cap. There is a deeper way to feel this without equations. Imagine four tuning forks you'd like to ring in phase so that pairs of them sing together whenever the referee asks, but the forks are mounted on a frame that twists. Lining up one pair nudges another pair out of step. You can pick a sweet set of angles that maximizes the overall harmony. This is the famous quantum advantage. Yet the frame prevents a perfect choir. That frustration is not sloppiness or noise, it is the structure of quantum compatibility. Some questions can be answered together cleanly, others jostle, and the jostling limits how strongly correlations can accumulate across the whole game. Now compare this with a fantasy world that still respects the no faster than light rule, but otherwise allows the most extreme non-local boxes. In that world, the same game could be won with implausible ease, and many communication tasks would become almost trivial. Partners could compute functions with nearly no messages once they met to compare notes. Our universe refuses that generosity. It gives you enough non-locality to certify entanglement, build secure keys, and generate certified randomness, but not enough to collapse communication complexity or to let correlations run roughshod over computational and thermodynamic sanity. Several independent principles hint at why. Information causality says the amount of usable information you can gain from me cannot exceed the number of ordinary bits I actually send, even if we share. Entanglement, stronger than quantum correlations, would violate that accounting. Macroscopic locality says that when you zoom out to large-scale averages, the world should still look classically consistent. Again, the wilder boxes would spoil that, and the familiar uncertainty trade-offs reappear here in a disguised, global form, distributing correlation strength so that pushing one link too hard weakens others. On the bench, Cyrelson's bound is not just a curiosity, it is a yardstick. When you observe a violation close to the quantum cap, you learn that your state is highly entangled and your devices are well aligned. When the number sags, you read off how much noise or miscalibration you must have. Device-independent cryptography literally turns that number into security guarantees. Surpass the classical ceiling by a comfortable margin, and you can extract secret bits, even if the measurement boxes are untrusted black bricks. Certified randomness generators do the same, converting the observed score into provably unpredictable digits. And in quantum networks and sensors, the bound tells engineers how far non-local boosts can go before diminishing returns bite, guiding designs toward regimes where each extra decibel of correlation actually pays off. There is also a quiet, conceptual payoff. Bell's theorem taught you that local hidden scripts can't explain quantum data. The no-signaling principle taught you that quantum weirdness can't be used to send messages faster than light. Cyrelson's bound stitches these together into a single attitude. Nature permits a disciplined surplus of correlation, enough to signal that reality's most accurate stories can belong to pairs rather than to parts, but it enforces a ceiling that keeps those stories compatible with causality, computation, and the logic of information. The universe, in other words, is generous without being reckless, and that attitude offers a human echo worth keeping. In your own projects, there is often a matching limit. Connections can amplify your reach, but if you try to align every relationship for maximal gain at once, the geometry of competing aims pushes back. The art is to find the sweet angles, harvest the surplus that's truly available, and accept that a well-designed ceiling is not an enemy of power, but the scaffold that lets power be used without breaking what it is meant to serve. Steering, guiding states at a distance. Imagine two people standing on opposite sides of a frosted glass screen. You trace different shapes on your side with a soft light, and on the other side, your partner watches shadows bloom into distinct silhouettes, not because your light slips through as a message, but because the shared stencil glued between the panes channels your choices into families of patterns they can sort. That is the feeling of quantum steering, the curious middle ground where entanglement lets you guide which ensemble of states appears for someone far away, without ever sending them a signal or deciding their individual outcomes in advance. In ordinary language, steering means this. When two systems are entangled, your choice of what to measure here carves the space of possibilities there into different, lawful clusters. Average over many runs, and your partner's statistics look the same no matter what you do, so causality rests easy. But if they later group their results by which question you asked, they find that their data were quietly sorted into different moods, as if your choice set the theme of their song, without dictating the notes. The technical object behind the scenes is a collection of conditional states on their side, the assemblage. And steering is the statement that no model where your partner merely held a pre-agreed stash of local states can explain how those conditionals line up across all your settings. This places steering between two better-known landmarks, weaker than the full-blown Bell impossibility that demolishes all local hidden scripts, but stronger than mere entanglement that might exist without letting one side reshape the other's ensembles. In fact, there is a tidy hierarchy. Some entangled states are not steerable, and some steerable states cannot violate a Bell inequality. The latter matters because steering is asymmetric. You can have one-way steering, where your apparatus can guide your partner's ensembles. But, given the same state, theirs cannot guide yours, an asymmetry born from details of noise, dimension, and what each device can actually ask. How do you see steering without equations? One family of tests uses sharp predictions about conditional spreads. If the two of you share the right kind of correlations, then by learning your outcome, your partner can predict paired properties of their system with a tightness that no locally prepared stash could permit. Violate those bounds, and you have steered them. Another line of attack crafts steering inequalities. Scores built from many setting choices that any local stash model would keep under a ceiling. Experiments with single photons, trapped ions, superconducting circuits, and even beams of continuous light routinely push past those ceilings, often in regimes where detectors catch nearly every event and measurement settings switch faster than any mundane influence could sneak across the room. The practical point is not parlor magic. Steering powers real protocols exactly because it sits in the middle of that trust ladder. In one-sided secure key distribution, for example, you only trust your own measurement device while treating your partner's detectors as black boxes. A clean steering violation is then enough to certify a secret key, something plain entanglement cannot guarantee, and full device. Independent methods would overkill. Steering also certifies that a channel preserves fragile quantum features you care about. If you can still steer after sending one half through a fiber or a chip, the link is truly quantum-worthy. In quantum sensing and communication, designers exploit steering to bias which kinds of states a distant node will effectively receive, not as a control knob that sends a message, but as a way to prearrange the palette of states that later classical communication will make useful. You see the same logic in sub-channel discrimination tasks, where steerable correlations let a receiver tell apart subtle transformations more efficiently than any classical playbook. There is a surprisingly geometric way to grasp the idea for two-level systems. Imagine all the states your partner can be steered into as a shape inside the familiar ball that represents their possibilities. The shared stencil fixes that shape, the steering ellipsoid, and your different measurement choices are like pointing to different locations on its surface. If the shape collapses to a point, you have no steering at all. If it balloons toward the boundary with symmetry, steering is strong. Skewed or squashed shapes reveal one-way behavior and sensitivity to particular questions. An equally deep but less visual insight is that steering and measurement incompatibility walk hand in hand. To steer, your side must ask questions that cannot be jointly answered by a single, classical-looking device. If your measurements could, all be simulated as pieces of one big compatible test, any apparent guidance would shrink to bookkeeping. Thus, witnessing steering is also a certificate that your measurement menu truly contains quantum-only dishes. All of this sits comfortably with the speed limit of the universe. Steering never lets you signal. Your partner's local statistics do not budge with your choice, and yet it still breaks the idea that their data could have been explained by a preloaded deck of local states. What you establish together is not a covert telephone, but a reservoir of structure that turns into advantage only when logs are compared later by ordinary means. The line it draws is practical. When you see steering, you know you are above the bar where entanglement pays dividends in cryptography, verification, and metrology, even if you are not at the rarefied heights required to tear up every local, realist story. When you don't, you know you must cool better, isolate better, or choose sharper. Incompatible questions to reach the regime where guidance at a distance becomes visible. And if you want a human echo to keep with you, take this. Steering teaches that influence need not be command to be real. Sometimes what you can do is choose the context that shapes which possibilities will later matter, laying down contours that turn scattered events into a coherent picture once the conversation finally happens. No strings are pulled across space, but a shared structure lets your choices here prepare meaning there. And in that quiet, causality-safe guidance, you glimpse a universe where connection is more about the patterns we can make together than about orders we can bark alone. Contextuality as a computational resource. Walk into a workshop where every tool behaves politely when tested alone, yet something uncanny happens when you use certain tools together. A wrench that fits perfectly in one sequence suddenly refuses. In another, a jig that aligns pieces only if you clamp a different edge first. And out of these context-dependent quirks, you discover you can build shapes no ordinary shop could make. That is the spirit of contextuality as a computational resource. When the outcome of a quantum question depends on the other compatible questions you ask alongside it, you are holding a kind of fuel that classical machines, whose parts have context-free settings, cannot burn efficiently. And it is this fuel that turns quantum processors from clever calculators into engines with capabilities that outstrip simulation on ordinary hardware. To see why this matters for computation rather than philosophy, start from what we can simulate cheaply. Circuits made only of those polite ingredients whose statistics admit a context-free description. Stabilizer states, Clifford gates, and the simplest measurements can be tracked on a laptop with bookkeeping tricks that scale gently. Add noise that keeps everything within that tame family, and the simulation still cooperates. In that regime, a quantum computer is like a workshop, whose tools never surprise you when combined, so a classical emulator can shadow every move. The moment you inject contextuality, the ledger breaks. There is no single assignment of pre-existing, measurement-independent outcomes that reproduces the patterns, and classical emulators must pay an overhead that balloon with the amount of non-classical fuel present. One crisp way to track that fuel is through quasi-probability negativity, an accounting system where ordinary processes carry non-negative weights, but truly quantum processes require negative or beyond probability entries. Those negative entries are a price tag for classical simulation. The more negativity you need, the more samples a classical algorithm must draw to keep errors small, and costs can explode. That is why the now famous trick for universal quantum computing looks the way it does. Keep the easy, efficiently simulable operations as your workshop frame and inject carefully prepared magic states that supply the missing non-classical juice. Distill those states until they are clean enough. Feed them into the circuit as catalysts, and suddenly gates that were impossible to get from polite ingredients alone appear as effective operations. Translated back to our theme, those magic states carry contextuality in a portable form. You import it when you need it, you spend it to cross computational frontiers, and resource theory lets you quantify the spend with monotones that never increase under free operations. A different vantage point comes from a style of computing where you front-load the entanglement and then compute by measuring. Prepare a big, regular web of qubits, and drive the algorithm by single-qubit measurements and small bits of classical feedback. The secret sauce is not the web itself, but the adaptive choice of questions, which makes outcomes live inside families whose relationships depend on which other compatible questions were asked. Contextual structure that a non-contextual model cannot reproduce without smuggling in exponential complexity. Put simply, the computational work is hiding in the pattern of which measurement, after which result, in which neighborhood. And it is contextuality that lets those patterns knit into non-classical transformations. This perspective clarifies a lot of engineering decisions. When researchers benchmark near-term devices, they increasingly look beyond raw gate fidelities to context budgets, asking how much contextuality survives noise and crosstalk and whether their compilers preserve it or accidentally wash it into classically simulable patterns. Randomized compiling and error mitigation techniques are praised when they lower coherent error without draining the negativity that algorithms rely on. Error-correcting codes are chosen not only for threshold, but for how they let you inject and move contextuality through fault-tolerant gadgets without letting it leak into uncontrolled corners where it becomes a liability. Even algorithm design reflects the accounting. Hybrid quantum classical workflows try to concentrate contextual subroutines where they add the most value and push the rest into classical pre- and post-processing. None of this says that more is always better. Contextuality is power only when it is structured. Spill it everywhere and you get chaos that noise exploits. Shape it with symmetries, measurement incompatibility, and smart scheduling, and you get speedups that show up as real wins, tighter sensing bounds, faster sampling of hard distributions, shorter circuits for chemistry problems, certifiable randomness, and keys extracted in ways no context-free model can fake. A helpful mental image is to think of computation as a supply chain. Stabilizer operations and classically friendly steps are your reliable trucks and roads. Contextuality is the special rail line that can cut across mountains, but only if the track is laid with care. Resource theory is the dispatch office that tells you how many railcars you have, how much load each can carry, and how the network must be planned so you don't run out of track in the middle of nowhere. There is also a deeper comfort here. Talk of quantum advantage often feels mystical until you pin down what the advantage is made of. Contextuality gives you the handle. An operational knob you can measure, increase by known procedures, conserve under known operations, and spend on tasks that provably resist context-free descriptions. When experiments report classical simulators, grinding to a halt as negativity or steering strength or incompatibility rises, that is not hand-waving, it is the accounting showing up on the invoice. And there is a softer echo you can carry back to ordinary thinking. In your own problem-solving, some insights only appear when questions are asked in the right company. Constraints considered together change what counts as a useful step. And the power you get from that reframing is not a trick, it is a resource. Used with intention, context turns a pile of separate facts into a machine that does more than the facts alone suggest. Used sloppily, it muddies. The quantum story simply sharpens the lesson with the authority of hardware. When outcomes are genuinely context-sensitive, the right ensembles of questions unlock capabilities no context, blind script can match, and the art of quantum computing is learning to bottle that sensitivity, meter it, and pour it exactly where doing so buys you the impossible. Collapse models. Imagine you are watching a flawless coin float in a silent room, not spinning, not falling, just suspended in a delicate superposition of heads here, tails there. And you ask yourself the question that standard quantum theory dodges with a polite cough. What exactly turns that cloud of possibilities into a single stubborn fact you can write in a notebook? Collapse models answer by changing the rules of motion ever so slightly so that the world itself, without observers, without apparatus tricks, occasionally and objectively nudges superpositions into definite outcomes. Rarely for single microscopic things, relentlessly for large many-part systems like coins, dust motes, pointer needles, and, by extension, everything you trust as solid. In the Ghirardi-Rimini-Weber picture, the nudge comes as a spontaneous hit, a sudden, random localization that multiplies the wave function by a narrow, bell-shaped envelope centered at some point in space. For one electron, such a hit would be fantastically rare. You could wait longer than civilizations last. But the rule includes an amplification mechanism. Every particle in a composite object is eligible for a hit, and the bigger the object, the more often some part of it gets jolted into place, dragging the rest along through their mutual ties. What you feel as everyday definiteness is simply the law of large numbers, applied to objective jumps. Continuous spontaneous localization takes the same idea and smooths it into a gentle, ever-present noise that couples to mass. Instead of sudden kicks, there's a universal jitter, a kind of random, whisper-quiet background field that continually pushes extended superpositions to shrink around one location. The mathematics behind that noise can be tuned to keep microscopic interference experiments intact, while making macroscopic delocalizations all but impossible. And with the right mass-proportional choice, the same amplification automatically appears. Many constituents mean many straws on the camel's back, and the camel sits down quickly. Both approaches are objective in the strictest sense. The collapse is not a story you tell after you look, not a bookkeeping update to your knowledge, but a physical event in the world. They also share two crucial promises that make them scientifically respectable rather than metaphysical. First, they are designed to forbid faster-than-light messages despite their randomness, so causality survives. Second, and this is the real payoff, they make concrete, testable predictions that differ from the perfectly linear, reversible evolution of orthodox quantum theory. You can chase those predictions in several ways. The easiest to picture is simple suppression of interference for heavy, slow, or widely separated paths. Build a matter wave interferometer for ever larger molecules or nanoparticles, and watch how the fringe visibility decays as mass, flight time, and path separation grow. Pure environmental decoherence can account for a lot of fading, but collapse models add an irreducible fade that remains even after you painstakingly remove stray gas, stray light, and vibrations. If that extra fade refuses to show up within the parameter windows the models require, you push their allowed settings into a corner. If it does show, you've caught nature in the act of choosing. There's also a tiny energy budget signature, because CSL's noise shakes systems a little. All the time, it predicts faint, universal heating, vanishingly small per particle, but potentially visible in the aggregate as extra motion in ultra-cold mechanical resonators, as additional broadening in spectral lines, or as weak X-ray emission from solids. Null results in exquisitely quiet experiments translate into upper bounds on how loud the collapse noise could be, while still doing the macroscopic job it's meant to do. Even big instruments built for other purposes help. If a universal jitter existed above certain levels, gravitational wave detectors would feel it as unexplained force noise. When they don't, those non-detections carve away chunks of the collapse parameter space. Levitated nanospheres held in optical or magnetic traps, cooled toward their motional ground states, offer another window, because any objective diffusion would show up against the near-perfect stillness as a telltale random walk. What sets collapse models apart from just another interpretation is exactly this accountability. You can write down the extra terms, you can estimate how quickly cat-like superpositions are pruned, and you can look for collateral traces that ordinary decoherence doesn't predict. And the field is mature enough to be nuanced. Variants consider whether the noise is truly white or colored in frequency, whether it couples strictly to mass density or to other observables, whether natural background fields might underwrite the collapse. Yet the core wager remains clean. Build a slightly non-linear stochastic twist into quantum dynamics, and you buy a world that does not need observers to end experiments. Of course, with new levers come new costs. Because GRW-style hits and CSL's noise are not derived from deeper known forces, they break the perfect energy bookkeeping of standard quantum theory by a hair's breadth. So model builders must choose parameters small enough to hide that cost in atomic physics, yet large enough to keep tables from smearing. Some, arguing from how photographic grains form or how latent images arise, have proposed stronger couplings, while others have pushed back with sharper experimental limits. The result is a live quantitative tug-of-war that tightens year by year. If you step back, you see three competing stories about outcomes now sit side by side with real stakes. Decoherence says the environment monitors superpositions so quickly that only certain stable records persist. Many Worlds says the unitary wave never collapses. Every outcome lives in a branching tapestry, and one result is your thread through it. Collapse says nature does the pruning for real, with tiny dice that roll everywhere all the time. Whichever story survives will be the one that keeps predicting correctly as our machines get colder, quieter, and more isolated. For you as a learner, the important thing is not to take the poetry on faith, but to follow the engineering. Ask what collapses, how fast, by what coupling, and where the heat, noise, or loss of visibility should appear. If future interferometers with truly massive objects keep perfect fringes far beyond current expectations, objective collapse will have to retreat. If the fringes die exactly where ordinary decoherence says they should, no more, no less, the orthodox picture looks fine. But if a stubborn, parameter-consistent haze remains after every known disturbance is tamed, we will be watching the world make up its mind in the way GRW and CSL quietly anticipated. And there is a human echo worth carrying out of the lab. Your decisions, too, feel like a slow accumulation of tiny pressures. Most days, your possibilities stay open, diffuse, and then, almost imperceptibly, some neutral, objective nudge pushes. One branch solid and the others fade. Whether that is illusion or deep rhyme, collapse models invite you to see a fact. Not as an edict from an observer, but as a physical event. The universe itself performs, everywhere, all at once, gently, but decisively, so that from restless possibility, a record can be born. Bohmian trajectories, hidden guidance beneath chance. Start with a daring picture. Imagine the world not as a haze that hardens only when you look, but as a river whose current is always there whether you watch it or not. What you call a particle is a tiny leaf carried by a flow you cannot touch, and the flow itself is shaped by a hidden map that spreads everywhere at once. This is the spirit of Bohmian mechanics, where every particle has a definite position at all times, and its motion is guided by the wave function not as a push you could feel, but as a rule for where the streamlines run. A law of motion that turns probabilities into paths. In this view, the wave is real and universal. It evolves by the usual quantum dynamics and, through a guidance rule, steers the configuration of particles the way a weather map's pressure lines steer the wind. If you knew the exact starting positions, you could in principle trace each leaf's journey without guessing. But in practice, you begin with ignorance about initial conditions, and when those unknowns are distributed in the same pattern that the wave assigns, the statistics of many leaves reproduce all the familiar quantum predictions, interference, energy levels, even the scatter of outcomes in measurement. So determinism underneath can coexist with randomness in the ensemble. The striking feature is how the guidance field bends routes around nodes, where the wave's amplitude drops near zero, and swirls around peaks where phase changes fastest. Launch particles toward a screen with two narrow openings, and their streamlines spread, weave, and gather into bright regions while avoiding dark ones. Not because each particle split and recombined, but because the flow lines drawn by the wave's landscape curve accordingly. In more complex settings, the same logic explains tunneling as paths that slip through a region. The classical map would forbid once the wave's landscape opens a new valley, and chemical reaction channels as highways in an invisible traffic plan that computational chemists can approximate and follow to estimate rates and branching without resorting to heavy symbolism. Measurement, which so often looks like a special event, becomes nothing mystical here. A measuring device is a big system, with its own particles and its own wave landscape. During the interaction, the joint wave spreads into branches that correlate different pointer positions with different microscopic configurations, but only the branch that actually contains the real configuration of all the particles continues to matter for what is recorded. The others are empty waves, still present in the bookkeeping yet powerless to change the pointer's path because they lack the stuff that moves. What, in standard stories, is called collapse appears here as ordinary branching, plus the simple fact that reality rides one branch instead of many. That said, the guidance is non-local in a very concrete way. When systems are entangled, the velocity of one particle can depend on where a distant partner actually is, because the wave that steers them lives on the combined configuration, not on separate islands. This is not a bug patched in after Bell's theorem. It is the price the theory pays openly to match the observed strength of distant correlations. Yet it still respects the ban on faster-than-light messaging, because the distribution of unknown initial positions washes out any controllable bias. You cannot use the guidance field as a telephone, but you can accept that the ledger of joint behavior reflects connections deeper than space. Critics sometimes point to surreal trajectories inferred by delicate probes and ask whether these paths are physical. The key is that those probes reconstruct averages of many weak touches, not the single run of a single leaf, and the guidance picture predicts exactly such averages because streamlines are features of the flow, not footprints, pressed into the riverbed. In carefully controlled experiments where atoms or photons are nudged scarcely at all, the reconstructed flow matches the theory's streamlines with good fidelity, reinforcing the idea that what is guided is the configuration through a real field of possibilities, not a mystery conjured at the detector. The approach generalizes beyond simple particles. Spin becomes part of the wave's internal structure that modulates guidance. Identical particles inherit a symmetry that prevents trajectories from violating the exclusion rules you learn in chemistry. In quantum field versions, the stuff that is guided can be particle positions that appear and disappear according to rules for creation and annihilation. Or it can be field configurations themselves, with the wave steering entire shapes rather than points. Making these stories sit comfortably with special relativity remains an active craft, often by letting a preferred slicing of time coordinate the non-local guidance while ensuring that no practical signal outruns light, a compromise that keeps empirical predictions aligned with standard quantum tests. The most delicate question is empirical distinctness. As long as initial positions follow the wave's probability profile, Bohmian mechanics reproduces the same numbers you would extract from other formulations for non-relativistic scenarios, which is why many treat it as a different ontology rather than a new set of experimental claims. Yet there are exploratory ideas. What if, in the early universe, the distribution departed from the standard one, leaving fossil traces in cosmic patterns? Or what if certain exotic measurements could expose empty wave influence under engineered conditions? None of these are settled, but they sharpen the posture of the theory by asking it to risk predictions rather than rest only on aesthetics. For you as a learner, the payoff of this hidden guidance picture is a sharpened intuition. Where standard, accounts speak primarily in terms of amplitudes and averages. Bohmian mechanics adds the image of a flow that you can visualize and compute, and this image anchors difficult processes, tunneling, branching, detection, in a single, continuous motion. It teaches you to ask new, concrete questions. Where are the nodes? How does the phase wind? Which channels carry most of the current? Which regions are shadowed by the wave's geometry? And how does interaction with a device redirect the flow into distinct basins corresponding to recorded results? And there is a gentler echo in all this for the way you steer your own life. You are not a passive flake in a storm, but neither do you write the weather. You move with a guidance field made by conditions around and within you, habits, contexts, shared structures, and while you cannot message the future into being, you can choose starting points and alignments that bend your path toward the clearings you value. Beneath the chance of your days, there is hidden guidance, not fate in the heavy sense, but a map you can learn to read, And once you see it, you stop seeing randomness as emptiness and start seeing it as a river whose current, if respected, will carry you where facts can be made and measured. Quantum Bayesianism, probability as personal belief in physics. Begin with a confession that feels both modest and liberating. Physics, as you actually use it, is not an oracle that stamps the future in stone. It is a disciplined way for you to place fair bets on what your own interventions in the world will return, and quantum Bayesianism, cubism, takes that working fact seriously enough to build a whole interpretation on it, saying that a quantum state is not a ghostly substance hovering over reality, but your personal catalogue of expectations about the consequences of the actions you might take. In this view, you are not a detached spectator, but an agent who chooses a measurement, better phrased as an action on a system, and then receives an outcome that becomes part of your experience. The numbers you assign in advance are degrees of belief, like a careful forecaster's odds, and after each outcome, you update those beliefs, just as any good Bayesian would, except that quantum theory places an extra empirical discipline on your bookkeeping. That extra discipline is the Born rule reframed. Instead of treating it as a mysterious law about waves collapsing, cubism treats it as a normative constraint that relates the probabilities you assign to different possible actions, a rule that tells you how to keep your web of expectations internally coherent when some questions cannot be asked together. If everyday probability theory is a set of rules that keep you safe from sure-loss bets, the quantum rule is an additional stitching that has proven necessary in our world whenever incompatible experiments are on the menu. You can picture the workflow without symbols. You decide what you might do to the system, which knob settings to choose, which detector to connect. You assign a prior spread of expectations to the outcomes of that action, and you also keep a standard reference questionnaire in mind, a fixed set of simple probes that, if you wished, could summarize any future experiment's expectations. The quantum rule then acts like a translator, demanding a particular relationship between your answers to the reference questionnaire and your answers to the actual one, a relationship carved by experience rather than by metaphysical fiat. Prepare badly, and the world will correct you with surprises. Prepared well, and your updates will be modest. This stance resolves several old puzzles, not by denying them, but by relocating their sharp edges. Collapse ceases to be a global physical jump and becomes a personal update. Your beliefs change because you learned something from your action. Wigner's friend-type scenarios stop looking like contradictions because different agents with different information can honestly assign different quantum states without anyone being wrong. Each state is a commitment about future experiences, conditional on what that agent knows, and the fear that quantum correlations must carry faster than light whispers evaporates because no one's local expectations can be made to depend on a distant choice in a way they could read without later comparing notes. None of this turns the world into mush or makes science a matter of taste. Cubism is not anything goes. It is be coherent and be corrigible, and the world enforces the second clause, bet against the Born rule, and in the long run, your devices, your statistics, and your bank account will complain in unison. Nor does cubism deny objectivity, it explains where it comes from. If many competent agents with similar experiences update their personal beliefs by the same normative rule, their expectations will tend to converge, producing the robust, intersubjective regularities you call laws, without pretending that those laws were written as a script on the things themselves. The reality that pushes back on you is not a spreadsheet of hidden values waiting to be read, but a partner whose responses to your actions have a stable character, and quantum theory is your shared grammar for making sense of those responses. The payoff of thinking this way is practical clarity for anyone who builds or uses experiments. Instead of fretting about where the wave function really is, you focus on designing actions that are informative for the questions you care about, calibrating your priors from earlier trials, and checking that your probability assignments obey the extra quantum stitching across incompatible setups. You stop asking whether a state is true and start asking whether your commitments are consistent, predictive, and ready to learn. It also reframes what randomness is. Not a fog imposed by nature to spite you, nor a mere ignorance about hidden facts, but the honest spread in your expectations before an action, with the spread shrinking or reshaping when new evidence arrives. In that sense, probability is not a property of the system, but a property of you in relation to the system, and the formalism is a user's manual for that relation. If this sounds uncomfortably personal for a hard science, notice how much of your best scientific practice already lives here. You already quantify uncertainty, you already revise models after data, you already treat measurements as choices with costs and payoffs, and you already judge colleagues by how well their expectations and updates stand the tests of coherence and prediction. Cubism simply states, with fewer euphemisms, that quantum theory's strange-looking rule is part of that same discipline. And there is a gentle, human coda to carry out of the lab. Living well also means acting under uncertainty with integrity, acknowledging that your beliefs are yours, that they can be made consistent, and that they must be willing to change when the world answers. The universe in this telling is not a stern lecturer reciting facts, nor a chaos of ungraded guesses, but a conversational partner, one that rewards careful questions with reliable guidance, so that your day-to-day acts of measurement, whether in a lab or in a life, are not about discovering a fixed script, but about refining a personal yet responsible map. A map that gets sharper each time you ask, listen, and adjust. Pusey-Barrett-Rudolph theorem. Must the wave function be real? Start with a blunt, slightly uncomfortable question you've likely carried without naming it. When you write down a wave function, are you describing something that exists out there, like a weather front you can't see directly, but that still pushes the clouds? Or are you merely tidying up your own expectations? A smart summary of what you think you'll see when you finally look. The Pusey-Barrett-Rudolph theorem steps into that tension and, under a clear set of assumptions, argues that the wave function cannot be just a summary, that different quantum states correspond to genuinely different physical situations, not merely different beliefs, so that changing the state is, in a deep sense, changing what the world is. To feel the core idea without symbols, imagine colored envelopes that hide tiny machines. You are told each envelope was prepared in one of two ways. Call them blue prep or gold prep. And your job is to decide whether those labels reflect reality or only bookkeeping. If the wave function were only information, it would be natural to think that some hidden internal configurations could arise from either prep, the way the same weather can be described with Fahrenheit or Celsius. In that picture, the two labels overlap in the space of underlying possibilities. Now duplicate the game. Take two envelopes prepared independently, one by you, one by a distant colleague, and later perform a joint test that, according to ordinary quantum rules, can sometimes identify the pair's labels with certainty. The PBR move is to show that if overlaps exist at the single envelope level, then independence of preparation lets you land, with non-zero chance, in a joint, hidden configuration that is compatible with several distinct label pairs at once. But the quantum joint test is constructed so that some of those pairs are guaranteed never to pass together. So your certainty-producing measurement would sometimes be forced to give an impossible answer. That contradiction means the overlap story cannot be right if you accept the independence premise and the standard predictions of the joint test. Translate the moral back to physics and you get this. If two quantum states can be prepared independently, then, unless you believe in conspiratorial links between those preparations, there is no single underlying real condition of the system that could be shared by both states. Distinct states map to disjoint slices of reality, what philosophers call a psiontic view, so that the wave function behaves less like a mere catalogue of guesses and more like a coordinate on the actual state of the system. It is important to see what this does not say. It does not tell you what the wave function physically is, a field, a relation, an informational object with teeth, and it does not forbid interpretations that keep probabilities personal, so long as they are willing to deny the key assumption that separately prepared systems have independent underlying conditions. That assumption, called preparation independence, is intuitively modest. If I flip a well-isolated coin in one lab while you flip yours in another, we expect the microstate under each coin to be whatever it is, without secret ties. But PBR shows that giving it up is the price of treating the wave function as purely epistemic. You might ask whether that price is worth paying. Some frameworks say yes. You can posit subtle correlations between nominally independent preparations, a kind of global web behind the scenes, or you can lean into agent-centered views where it's acceptable for different observers to assign different states without positing any observer-independent real wave. But once you take those roads, you owe new explanations. For example, how those correlations arise and remain undetectable in ordinary tests, or how multiple agents keep their stories stitched together in shared experiments. PBR doesn't close those paths, it simply raises the bar by turning a fuzzy philosophical preference into a crisp fork in the road. On the constructive side, the theorem harmonizes with stories that already treat the wave function as real in some sense. Pilot wave. Dynamics gives it the role of guide. Collapse models make it the seat of objective jumps. Algebraic approaches treat it as a faithful summary of a system's actual disposition. And it provides a cleaner answer whenever a student asks, is there anything there that the state is pointing to? Yes. If you accept independent preparation, different states point to different theirs. Beyond metaphysics, the result has practical echoes. State reconstruction in the lab, tomography, stops looking like inferring a private opinion and more like diagnosing a patient's true condition. Error analysis gains teeth because preparing the wrong state is not just a bookkeeping sin, but a physical mismatch. And in quantum cryptography, where the security of protocols often leans on the uniqueness of prepared states, the PBR narrative supports the intuition that confusing one state for another is confusing one physical situation for another, not just swapping labels. Still, intellectual fairness demands that you carry the caveats with the confidence. PBR presumes the quantum predictions for the special joint test are right. They are, within experimental error, presumes independent preparation is meaningful, most laboratories are built on that idea, and presumes that the hidden level description, if any, assigns ordinary probabilities to underlying conditions, rather than wildly contextual or retrocausal rules. Relax those pillars, and you can rebuild epistemic shelters. But each shelter needs new beams, and the weight of everyday practice leans the other way. The psychological payoff of the theorem is quiet but real. It invites you to treat your calculations with a touch more ontological respect. When you change a state, you are not merely changing your mind. You are, in the implied structure of the world, changing the system's address. And even if you remain agnostic about the furniture of that address, you can appreciate the new clarity about the cost of claiming it's just information. In the end, the PBR message is not that philosophy is over, but that the question, must the wave function be real, is no longer a matter of taste alone. It is a technical question with technical hinges. And once you see where those hinges are, independence of preparation, the architecture of joint measurements, the refusal of overlaps, you can ask sharper, fairer questions of your own work. Which assumptions am I prepared to keep? Which am I willing to pay to drop? And how will I know in the data that I've kept the accounting honest? Positive operator-valued measurements versus projectors. Measuring beyond. Yes or no? You've been taught to treat a measurement like a door with two positions, open or shut, yes or no. And that picture is comforting because it feels clean, but the real craft of quantum measurement is closer to a dimmer switch with many stops and a side channel that lets you peak without slamming the scene to a halt. In that craft, projector measurements are the crisp on-off questions that sort a system into perfectly sharp categories and replace it with a matching sharp state, while positive operator-valued measurements, POVMs, are the broader family of questions you can actually ask in the lab when you want more nuanced information, when your detectors have imperfections, or when your goal is to extract useful clues with less damage. and understanding the difference turns measurement from a single note into a full instrument you can learn to play. Projectors are idealized spotlights. Point one at a system, and you get a definitive answer tied to a specific property. This state or that, this path or that. And the act of asking forces the system into the spotlight's beam pattern. It is a great way to certify a category. But it is also a blunt tool because it leaves no room for close to, or partly this and that, or I learned a bit but didn't wreck the rest. POVMs generalize the question itself. Instead of a binary cut, you can design a measurement with 3 outcomes, including an honest inconclusive, or with several outcomes that carve space into finer sectors, or with soft outcomes that carry partial evidence. You can even design measurements that, by intent, trade sharpness for gentleness, learning a little while disturbing little, so that you can keep probing the same system again. Think of a photon counter that sometimes misses a photon and sometimes clicks all by itself. The physically meaningful question isn't just photon yes, no, it's click, no click, or noise, and you can fold that into a 3-outcome POVM that models reality and lets you make fair inferences. Or imagine trying to tell 2 almost identical states apart. If you insist on a sharp projector question, you'll make frequent mistakes. But if you allow a 3rd outcome that admits I can't tell, there are well-designed POVMs that guarantee 0 misidentifications at the price of sometimes shrugging, a trade that engineers actually want. In optics, if you try to read out 2 non-compatible quadrature properties at once, a projector can't help you because the questions clash, but a cleverly built POVM collects joint information about both, adding the minimum noise the world demands. In sensing, if you need to keep a fragile state alive, you can arrange a sequence of gentle, many-outcome POVMs that nibble away at your uncertainty rather than gulp it in one disruptive gulp. A useful way to hold this in your head without math is to think of a measurement as 2 linked pieces. A rule that assigns a probability to each possible outcome, and a rule that tells you how the system is transformed when that outcome occurs. Projector measurements fix both parts strictly, sharp probabilities and a sharp post-measurement state, whereas POVMs let you shape the menu of outcomes freely, and for each outcome, you can choose a transformation that fits your task, from barely touching to fully resetting. This broader object, a family of outcomes each with its associated state update, is what experimentalists actually implement. And it is why the beyond yes-no language isn't a philosophical flourish, but a practical blueprint. There is a deep guarantee behind the practicality. Any POVM you can write down can be realized physically by temporarily enlarging the stage. Let your system interact with an extra, well-prepared probe. Ask an ordinary projector question on the combined pair and then ignore the probe. The many-outcome, gentle, or lossy behavior you wanted falls out of the way you coupled the two and the way you processed the probe's answer. This construction, which theorists call a dilation, tells you that generalized does not mean imaginary. It means implemented with a helper and a good plan. Why would you ever return to projectors then? Because when the question aligns perfectly with your goal, a projector gives maximum certainty and creates a clean record. Think of reading a digital memory bit or checking whether an atom is in a particular energy level for a clock. But when your task is to extract the most information per experimental dollar, to discriminate among several hypotheses, to track dynamics without derailing them, or to cope honestly with detector imperfections, POVMs are the language that keeps your inferences honest. They let you count nearby evidence. They let you say, I have partial support. And they let you design measurements that are optimal for the decision you genuinely care about. Consider the common problem of minimum error state discrimination. You know a system was prepared in one of several known states, and you must guess which. Projectors lock you into a particular, often suboptimal, partitioning, but tailored POVMs provably minimize your average mistake rate, squeezing every drop of distinguishability the states offer. Or consider tomography, where you reconstruct an unknown state. You could pile up many separate projector settings, slowly covering the space, or you could design a single, well-chosen many-outcome POVM that samples the space evenly and gets You there faster with fewer experimental configurations. When budgets and stability matter, fewer configurations mean fewer calibration pitfalls. These choices reach into computing and communication too. In error-correcting codes, you sometimes need soft information, not just a hard pass-fail, because feeding a decoder with likelihoods rather than absolutes improves performance. And POVMs are precisely the way to convert analog detector behavior into principled likelihoods. In secure key distribution, you may want to certify that your measurement really matches the intended question, even in the presence of imperfections, and modeling your actual device as a POVM instead of pretending it's ideal gives you security. Proofs that reflect the device you are holding rather than an imaginary twin. You might worry that allowing all this freedom makes predictions mushy, but the opposite is true. The rules that turn states into outcome probabilities are fixed and tested. The generalization lives in which question you pose, not in whether the world answers fairly. And once you choose a POVM, its outcomes tie down your inferences with the same statistical discipline as any sharp measurement. What changes is your ability to tailor that discipline to the shape of the problem. Do you prefer occasional, "I don't know," to frequent, silent mistakes? Do you prefer many gentle peaks to one loud look? Do you need outcomes that cover a space evenly, rather than slice it along one axis? Do you want a detector model that accounts for real inefficiencies, so your error bars make sense? Each of these is a measurement design question, and POVMs are the answer key. The philosophical relief is subtle but valuable. Once you accept that, measurement is not one hammer, but a drawer of well-labeled tools. Many confusions evaporate. You stop blaming the world for failing to deliver a single, perfect truth on demand, and start respecting the bargain every experiment strikes. Ask a narrow, certifying question and pay with disturbance. Ask a broad, gentle question and pay with grain. Design a many-outcome question and harvest structured evidence that reaches beyond yes, no. The choice is yours, and the discipline is to make the choice explicit. And there is a human echo in this, too. Your own inquiries, scientific, personal, moral, are rarely well served by rigid binaries. Often the smart move is to design better questions, ones that allow partial but useful, uncertain but honest, not now but later. And this much we can say: projector questions still have their place when a decision must be taken cleanly, but most of your progress comes from richer menus of outcomes that let learning accumulate. Measuring beyond yes-no is not a retreat from truth. It is a more precise way of approaching it. One carefully designed action at a time with enough gentleness to keep the subject alive for the next question. Symmetric, informationally complete, positive operator valued measurements. Imagine you are handed a perfectly balanced color wheel and told that with only a small, fixed number of carefully chosen swatches, you must capture any shade a painter could mix, no matter how subtle the blend. Symmetric, informationally complete measurements are the quantum version of that wheel. A set of outcomes arranged so evenly that the probabilities you record against them contain just enough information. And, not a bit more, to reconstruct the state uniquely, turning the messy problem of "what is this system really?" into a clean, well-conditioned decoding task that a laptop or a mind can carry out without gymnastics. In ordinary measurements, you often sample along a few privileged directions and then stitch together many settings to get the full picture. Here, you select a single, exquisitely designed menu with exactly as many outcomes as there are independent numbers in the state. And because each outcome is equally tilted with respect to the others, the menu treats all possibilities fairly. For a two-level system, this looks like 4 outcomes pointing to the corners of a tetrahedron on the block sphere. For a higher dimensional system, it becomes a constellation of outcomes that form the corners of a regular simplex in the abstract space where states live. The result is that every quantum state maps to a unique set of outcome probabilities, and the map can be inverted with a simple linear recipe instead of a delicate iterative search. Why does this matter? Because reality gives you data through detectors with imperfections, drifts, and budgets, and you want a scheme that remains stable when the world wiggles. Symmetry buys you that stability. When the outcomes are arranged in perfect balance, small errors smear evenly rather than shattering one coordinate while leaving others pristine, which means your reconstructions are kinder to noise. Informational. Completeness buys you efficiency. You do not need to rotate through dozens of incompatible settings or rebuild the apparatus when your target changes. You ask your one good question and learn everything learnable from its answers. There is also a conceptual payoff that hides in plain sight. If you agree to express states as probability lists over this special menu, then the familiar quantum rule for predicting outcomes becomes a relation between probabilities, a refinement of the everyday law that relates priors, conditionals, and marginals. In that light, quantum theory looks less like a foreign language and more like an accent added to ordinary uncertainty, a disciplined way to keep your web of expectations consistent when some questions cannot be posed together. The symmetric menu acts as your standard reference, a ruler against which all other questions are calibrated. On the lab bench, this turns into tangible wins. Tomography becomes a single-setting experiment with many readout channels rather than a parade of reconfigurations, which slashes alignment headaches. State discrimination gains sharper strategies because you can project your evidence onto a basis tuned to spread differences evenly. Detector calibration becomes more honest because your model matches what the hardware actually delivers. Multiple outcomes with partial confidence, rather than forcing a binary idealization that never quite fits. And in cryptography or randomness generation, where you need to certify that your source really produces a wide variety of states, a symmetric menu exposes bias quickly because every direction in state space is probed with equal sensitivity. There is beautiful geometry underneath that you can see without symbols. Imagine the space of all allowed states as a rounded shape, a ball for two-level systems and a higher dimensional cousin otherwise. The symmetric outcomes mark the vertices of a regular polytope inscribed in that shape, and your unknown state is recovered by asking how much the data lean toward each vertex. If the polytopy were lopsided, many very different states would cast similar shadows, but symmetry prevents that degeneracy. Different states pull the needle in measurably different ways. The design problem then becomes, find the most evenly spaced set of corners so that the shadows are maximally informative. That is exactly what symmetric informationally complete means. Are such designs always possible? For the simplest systems, the answer is yes, and the constructions are explicit. In larger systems, we have vast families built by shifting and phasing a single seed pattern, the way musical themes generate variations, and decades of work have produced explicit examples in many dimensions. The general existence is a standing conjecture rather than a theorem, but the sheer weight of constructions and numerical solutions has made the symmetric menu a working tool rather than a dream. Implementations follow the physics you have at hand. In photonics, you combine path, polarization, and phase to engineer 4 or 9 or 16 evenly balanced clicks. With trapped ions and atoms, you choreograph laser pulses that map the symmetric outcomes to distinct fluorescence patterns. In superconducting circuits, you shape microwave tones so that each outcome corresponds to a distinct ring in the readout plane. Every platform has learned to approximate the ideal to the point that symmetry's benefits show up in the error bars. There is a subtle bridge to other complete designs that you may have heard about. Mutually unbiased bases slice the world into several clean, dichotomy-like views, whose results do not predict each other. The symmetric menu does something complementary. Rather than cycling through many bases, it fixes one finely grained basis that spreads attention evenly. In practice, when stability matters more than switching speed, the single symmetric menu wins. When hardware reconfiguration is cheap and you want redundancy, many unbiased bases can be convenient. The art is to match the geometry to the job. Beyond the bench, the symmetric menu has changed how some researchers think about the foundations. When you write states as probabilities over this fixed set, the exotic algebra of operators recedes and the emphasis shifts to relations among probability lists. Certain negativity indicators that signal quantum advantage become easy to compute in this representation. so you can track non-classical resources as they flow through a computation or a communication link without drowning. In Matrices, even the discrete version of the old phase space picture, the Renormalization, adopts a cleaner shape when you choose the symmetric menu as your coordinate grid, which makes the boundary between classically simulable circuits and truly quantum routines easier to draw. If you want a more tactile image to carry out of all this, think of the symmetric menu as a calibration card. A photographer slips into a scene. With a single snapshot, the card's equally spaced color patches let you correct the entire palette. Here the card is embedded in the measurement itself, and the correction is the full reconstruction of an unknown quantum state from one good shot. You still need care. Light must be even, the lens must be clean, but the geometry of the card is doing heavy lifting you would otherwise have to fake later in software. And there is a softer echo for everyday learning. The questions you ask shape what you can know, so it pays to design a small set of balanced questions that, together, touch every relevant direction of a problem. Ask only sharp, yes, no questions, and you will keep flipping the setup, never catching the whole picture. Ask too many unbalanced questions, and you will drown in redundancy. The symmetric design says, choose a minimal, evenly spaced set that lets you rebuild the world you are studying from the answers you get, and let the symmetry carry you when noise and time push back. In physics, that strategy becomes a sick problem. In a life, it becomes a way to notice well, update honestly, and move forward with a map that is both compact and complete. Weak values, reading the in-between, gently. Imagine trying to learn about a skittish animal without waking it. You'd rest a feather on its fur, note the faintest twitch, and step back, repeating the ritual many times until a pattern emerged. Weak values are the quantum version of that feather touch, a way for you to ask a system about an observable so gently that you barely disturb it. Then use a clever filter at the end, post-selection, to keep only those runs where the system finishes in a state you choose, and from the tiny average shift of your meter on those filtered runs, infer an in-between number that often looks strange at first glance, yet encodes honest operational information about how the system's possibilities interfere between your initial preparation and your final check. The protocol feels simple in your hands. You prepare a system in some known input state. You couple it weakly to a meter, a beam position, a phase, a pointer needle, so that the coupling is too feeble to yank the system into a sharp eigenstate. And then you perform a strong, ordinary measurement, not of the same quantity, but of a second one that defines which histories you care to keep. On the subset of trials that land in your chosen final state, the meter's average nudge reveals the weak value, a conditional signature of the process that depends on both the beginning and the end. Because the coupling is tiny, each single readout is buried in noise, but over many trials a shift emerges that you can calibrate in ordinary units. The surprise, the part that grabs headlines, is that these weak values need not lie within the familiar range of eigenvalues. Prepare and post-select almost orthogonal states, and the pointer's average can move as if the system momentarily possessed a value far beyond the usual limits, or even of the wrong sign. But this is not a case of nature breaking its own spectrum. It is an interference effect in your statistics. By conditioning on a rare final outcome, you skew the ensemble so that the small meter shift per run is multiplied by the rarity of acceptance, and the resulting conditional average can live outside the naive bounds while still being derived from entirely ordinary dynamics. What makes weak values more than a curiosity is their practical leverage in regimes where you fight technical noise. If what buries your signal is slow drift, detector 1F noise, or limited resolution, then trading a large fraction of your data for a few amplified, well-separated pointer shifts can improve your ability to see a tiny effect, even though, when you count every photon or every shot, the ultimate information theoretic limit on precision remains the same. That's why optical experiments have used weak value amplification to detect minuscule beam deflections, to measure tiny birefringence or polarization rotations, and to resolve subtle transverse shifts of light near interfaces. The amplified shift spreads the effect over many pixels where technical noise is flatter, turning lost in the least significant bit into plainly visible above the baseline. Beyond amplification, weak values serve as gentle probes of structure you cannot access with a single sharp look. By weakly sampling one quantity and then reading another strongly, you can reconstruct phase gradients in a wavefront, map tiny currents within a probability cloud, or even perform direct measurements of certain state features that usually require heavy, iterative tomography. The trick is always the same: touch lightly, condition wisely, average long. If you keep the coupling continuous in time rather than in a single pulse, you can stitch those tiny peaks into a movie of quantum trajectories, watching a qubit wander under the combined push of your weak monitoring and its own Hamiltonian dynamics. If you also use the final outcome as information when smoothing that record, retradicting as well as predicting, the weak value formalism tells you the most reasonable estimate for what the meter would have read at each intermediate moment. Given what you knew then and what you learned later, this is a sober calculus, not mysticism. You are simply folding two boundary conditions into your best estimate for the middle, the way weather forecasters improve yesterday's map with today's satellite pass. Because the coupling is gentle, weak measurements let you ask partially incompatible questions in sequence without destroying the subject of study. You can weakly sample a component of spin, then another, and infer correlations that would be inaccessible with two sharp back-to-back projective measurements. Engineers exploit that to diagnose crosstalk and coherent errors in processors, to track slow drifts in resonators, and to design feedback that nudges a system toward a target without jolting it off course. It is crucial, though, to keep the bookkeeping honest. Post-selection is a filter that discards most runs when you aim for large amplification, so the price of a dramatic pointer shift is a lower data rate. If you count the cost correctly, how many trials you needed, how often you reset the device, then weak value strategies do not beat the fundamental shot noise or quantum Fisher information limits. They shine when real-world detectors fall short of those ideals, when your enemy is not nature's randomness, but your hardware's quirks, and they're the method's ability to reposition signal into a friendlier part of your instrument's response can deliver cleaner answers for the same experimental budget. The interpretational debates that swirl around weak values often evaporate once you hold tight to what is actually measured. A weak value is not the system confessing a secret property it had all along, nor a loophole through which it has impossible attributes. It is a conditional expectation for your meter's shift, given your chosen preparation and your chosen post-selection. A number that tells you how the meter will respond if you repeat the whole dance many times. Call it a contextual property of the measurement chain, if you like. What matters operationally is that it is reproducible, calibratable, and predictive under the protocol that defines it. In platforms as different as single photons, trapped ions, cold atoms, and superconducting circuits, the gentle touch recipe keeps paying dividends. Tiny delays in interferometers become measurable as large phase-to-position translations. Faint dispersions in materials leave legible fingerprints, and the dynamics of metastable states can be sampled mid-flight without collapsing the very process you wish to watch. In metrology, weak values let you repurpose indifferent detectors by shifting the burden from absolute accuracy to differential sensitivity. In control, continuous weak monitoring supplies the streams your algorithms need to stabilize otherwise fragile states. And in pedagogy, the method gives students an intuition pump. By literally seeing a pointer creep in response to a chosen pre- and post-selection, they learn that quantum predictions are not only about final clicks, but also about the structures that knit causes to effects across time. If you want a clean mental picture for why the numbers can be weird yet meaningful, imagine your meter's pointer as a soft brush touching a vibrating string. A strong measurement slams the string against a fret and reads a note you expect. A weak one lets the string ring while the brush picks up a phase-dependent tickle. By listening only to performances that end on a particular chord, your post-selection, You isolate a delicate interference pattern in the brush's motion that would be averaged away otherwise. The larger than usual sway you sometimes hear is not the string-breaking scale. It is your playlist emphasizing a rare cadential path where the phases add conspicuously. And there is a human echo in the method worth holding on to. When the thing you care about is easily damaged by blunt inquiry, an idea half-formed, a relationship under stress, a system poised on a threshold, the wiser move is often a sequence of light touches paired with careful selection of which responses you dwell on. You learn from small, gentle cues. You condition on cases that reveal the structure you seek, and you accept that big insights can be extracted from hints if you are patient with averaging. Weak values, read this way, are not merely a clever trick in the lab. They are a reminder that knowledge sometimes grows best when you resist the urge to force a decisive answer and instead learn to listen for the in-between. Protective measurement. Sampling a single system's state. Imagine wanting to weigh a snowflake without letting it melt, to learn something steady about a single fragile thing while leaving it essentially as you found it. Protective measurement is the disciplined way physics tries to do exactly that, arranging conditions so that you can read the average value of an observable directly from one quantum system, not a crowd, by touching it so gently and so intelligently that the usual either this or that jump never happens, and a slow, dependable shift accumulates in your meter instead. The strategy has three moving parts you can picture without symbols. First, you protect the system in a specific state so it is hard to knock elsewhere. Typically a non-degenerate energy state separated by a gap, or a state stabilized by active guarding that repeatedly checks, "Are you still here?" and nudges it back, a quantum Zeno kind of shepherding. Second, you couple a detector to the system so weakly that any single instant barely tugs, but you keep that feather-light coupling on for a long, controlled time. Third, you watch the detector's pointer creep. The tiny influence integrates, like a steady drip filling a cup, and the final displacement is proportional to the expectation value of the quantity you cared about for that very state. In ordinary measurements, you either get a sharp eigenvalue and collapse the state, or you average outcomes across many identical trials to reconstruct a mean. Here you do neither. You retain the state and let the average write itself onto the pointer in one elongated pass. Why doesn't this violate the usual trade-offs, or the rule that incompatible questions can't be answered together? Because you're not trying to squeeze two sharp facts out at once. You're reading one gentle, calibrated statistic under conditions that keep the state nearly unchanged. The protection makes side routes energetically or dynamically implausible, and the adiabatic, weak interaction suppresses the violent back action that would ordinarily yank the system into a new configuration. In practice, this means you need prior structure. You must know enough about the system to protect the right state. You must choose an observable that won't sabotage the protection, and you must give the interaction long enough to accumulate signal without giving the environment time to spoil the plan. Done well, the post-measurement state is, to very good approximation, the same as the pre-measurement state. And yet your meter now carries a readable imprint of the state's property. This is not a loophole for magic. If the state is degenerate and unguarded, the method fails. If you try to read too strongly, you lose protection and revert to ordinary collapse. If you demand several incompatible averages at once, you must repeat the procedure with resets, and if noise, drift, or stray couplings hover, the slow creep can drown. But when the engineering is kind, the payoff is a new style of knowledge. Expectation values, local densities, field samples, occupation, fractions become accessible from a single protected specimen. Conceptually, this is striking because it sits between two familiar extremes. Unlike a projective measurement, it does not rip a crisp number from the system at the price of destroying the very state you were studying. Unlike brute force ensemble, averaging, it does not require many copies prepared the same way. It is a third path where control and patience replace repetition and collapse. At the bench, you can see what it's good for. Non-destructive checks of qubit initialization, confirming that your one device really is in the target state before you build on it. In situ sampling of local fields with a single trapped ion, or defect center, letting a solitary probe report an average without being spent. Verification that a prepared atomic level or vibrational mode is genuinely occupied as intended, so you don't re-prepare blindly. And calibration routines where the state is precious and must survive the diagnostic. The protection itself can be achieved in multiple ways. Energy gaps and adiabatic ramps are the textbook version. Let the system sit in a specific eigenstate and turn the coupling on and off so gradually that it never finds a reason to leave. Active protection is a newer craft. Use frequent, gentle, "Are you still here?" checks or feedback to keep the state pinned while the pointer listens. In both cases, the same intuition applies. Keep the door open, just a crack, long enough for an imprint to form, never wide enough for the state to slip out. Because the meter's shift is proportional to an expectation value, some have claimed this measures the wave function of a single system. And you should hear that claim with both curiosity and caution. If you already know which state you're protecting and you choose a rich menu of observables across repeated runs, you can indeed map out many features of that state without ever collapsing it in the process. But if you start ignorant, you cannot conjure a full, unique wave function from one protected specimen in one shot. Protection requires enough prior knowledge to target the right state, and reconstruction still needs a structured set of gentle queries. So protective measurement is not a free pass to complete knowledge. It is a precise protocol for reading certain averages from one system in a way that leaves that system usable afterward. Notice also what it doesn't break. It doesn't let you send messages faster than light. Your partner's local statistics don't budge because you protect your state. It doesn't defeat the no cloning rule. You never copy an unknown state. You just sample a feature. And it doesn't nullify uncertainty. You don't claim simultaneous sharp values where nature forbids them. It does, however, sharpen a philosophical question about what a quantum state is. If you can, under the right guardrails, read an average property from a single system while leaving that system essentially alone, the state begins to look less like a mere catalogue of your beliefs and more like a structured disposition that a lone specimen genuinely carries. Skeptics reply that what you really measure is a property of the protected pair, system plus guardrails, because the very act of protection builds context into the outcome. Both readings can be held honestly, and the virtue of the method is that it makes the debate empirical. It pushes you to specify what protection you used, what you read, how close the state stayed to itself, and where any unavoidable disturbance leaked. As a working scientist or an attentive learner, the lesson is practical. If the thing you study is rare, expensive, or easily damaged, you don't have to choose between ignorance and destruction. You can design long, quiet couplings that let small truths accumulate while the state endures, then reuse the same specimen to ask the next careful question. And there's a softer echo for ordinary life in that engineering stance. Sometimes the right way to understand is neither to pounce nor to poll a crowd, but to protect a single relationship, a single habit, a single thought, and let a steady, almost imperceptible conversation reveal its average character. Patient contact, not force, yields a reading that lasts, and when you finally set the instrument down, you find the thing you cared about is still there, ready for what comes next. Quantum tomography, reconstructing the invisible. Stand in front of a blank wall and wave a flashlight through a stencil, while your friend photographs the shadows from different angles. No single photo tells you the object's shape, but together, the silhouettes begin to agree on a form, and with enough disciplined views, you can reconstruct the thing you never directly saw. This is the spirit of quantum tomography, a careful ritual where you ask a quantum system many compatible questions, record the pattern of answers, and then solve an inverse problem to rebuild the state that would have made those answers most likely, turning invisible structure into a usable model you can trust. You begin, always, with a choice of views. For a two-level system, you might measure along several axes. For light, you might scan field quadratures with a local oscillator. For many qubit registers, you spread questions over tailored patterns that probe different combinations of components. What matters is that the set of questions covers the whole space of possibilities in a principled way, neither too sparse to miss features, nor so redundant that you drown in correlations. And that the hardware asking them is honest about its imperfections. Raw counts come back as tallies, not truths, so you face an inversion step with two core paths: a quick linear recipe that inverts the mapping from states to probabilities and yields an initial estimate fast, and a more careful statistical fit that respects physical constraints like positivity and unit trace while blending information across settings. The second path often uses maximum likelihood ideas, or Bayesian updates, to find the state that best explains the data you actually collected, rather than the data you wish you had. And because noise and drift are real, you attach error bars, or credible regions, to say how sure you are about each feature. As systems grow, you learn to negotiate the curse of dimensionality with craft rather than brute force. When you know your target should be close to a simple form, say nearly pure or low rank, you can trade the full scan for compressed strategies that sample a clever subset of questions, yet still allow accurate recovery. When you only need selected properties, fidelity with a reference, or a handful of observables, you can skip reconstruction entirely and estimate those features directly with randomized measurements that keep the workload manageable. When you do want a broader picture without the full burden, you can deploy classical shadows, short sequences of random probes whose outcomes, combined with simple post-processing, let you predict many different expectation values with guarantees on average performance. All of this assumes your measuring devices tell the truth. In practice, they have biases, crosstalk, missed clicks, and drifts in gain, so modern labs often run detector and process tomography alongside state tomography. The first characterizes the actual menu of outcomes your detectors realize. The second maps how a gate or channel transforms states, and a newer, self-consistent approach called gate-set tomography stitches state, gate, and measurement descriptions together in one fit. To avoid circular assumptions, when you adopt such self-calibrating routines, you confront gauge freedoms, different internal descriptions that make the same external predictions, and you learn to report only gauge invariant features like average errors or specific figures of merit, keeping the physics tied to what experiments can truly distinguish. The workflow is a chain whose links must each be sound. Choose a quorum of questions whose geometry is well conditioned. Collect enough repetitions to tame randomness without inviting drift. Model the detectors honestly. Invert with a method that respects the physics. And validate the result with cross-checks you did not train on. Holdout settings, likelihood ratio tests, or bootstrap resampling that probes the stability of your conclusions. When something looks too sharp to be true, it often is, and the cure is usually more evenly spaced views, better accounting for background counts, or a gentler prior that discourages overconfident spikes the data cannot support. In photonics, you might watch a reconstructed phase space portrait settle into a shape whose dips betray non-classical features. In trapped ions, you might use tomography to verify that an entangling gate actually prepared the target pair with the promised correlations. In superconducting qubits, you might catch a slow phase drift by seeing the reconstructed state rotate over hours and then fix it at the source. In solid-state defects used as sensors, you might confirm that repeated preparations are consistent, day to day, turning a single bright point of light into a calibrated probe with a documented state. Because you never have infinite time or perfect stability, adaptive strategies become your ally. You take a first batch of data, update an interim estimate with error bars, and then aim the next questions where they will shrink uncertainty fastest, toward regions of state space where your current model is most indecisive. This feedback loop compresses effort, much as a good photographer adjusts exposure and focus after a test shot, rather than blindly bracketing every setting. Importantly, tomography is not a fishing expedition for hidden absolute properties. It is a disciplined way of building a predictive model consistent with the statistics your procedures produce, one that lets you forecast what future measurements will show and diagnose when hardware steps out of line. Expressed in plain terms, you are manufacturing a reliable surrogate for the system that you can hand to colleagues. If you do these things, expect those outcomes to within these uncertainties. When you move from single systems to dynamics, the same inversion logic recurs. You probe how inputs turn into outputs, reconstruct a map, check that it respects physical constraints like complete positivity, and then summarize it with interpretable parameters, coherent rotations, relaxation rates, dephasing times that feed back into design. And when you suspect your devices influence one another, you extend your questions to catch crosstalk and stray coupling, because a good reconstruction should reveal not only the ideal you aimed for, but the shade of reality that arrived. Ethical clarity matters too. A reconstruction is only as honest as your willingness to report its limits. Publish the choice of questions, the sizes of your datasets, the model for your detectors, the method you use to invert, the regions of confidence, and the cross-validations you passed and failed. When you enumerate these with care, your invisible picture earns the right to be believed and reused. When you don't, the next team wastes months chasing ghosts that were artifacts of a narrow scan or a silent bias. Conceptually, there is a quiet satisfaction in quantum tomography because it transforms a philosophical worry, we never see the state, into a practical craft. You may not see it, but you can reconstruct it sufficiently to act, and you can quantify how sufficient is. What results is not a metaphysical portrait, but a control panel. Push this, expect that, fix here, improve there. And for your own thinking, there is a gentle echo worth keeping. When a problem is opaque, you are not condemned to guess or to give up. You can choose a balanced set of views, gather imperfect evidence carefully, and solve an inverse problem with humility built in, updating as new light arrives. In physics, the object is a quantum state. In a life, it might be the shape of a habit or the outline of a plan. Either way, reconstruction is the art of making the invisible actionable without pretending that it was ever directly seen. An art whose power comes not from a single dramatic measurement, but from many small, honest glimpses that, together, tell the truth. Density matrices. Ignorance versus entanglement. There are two very different reasons a picture looks hazy. Sometimes your hand wobbles the camera, and sometimes two scenes are double exposed on the same frame. Density matrices are the language physics, uses to tell these blurs apart without lying to you about what you can and can't know, because they describe quantum states in a way that works, whether your uncertainty is just you not knowing which preparation was used, ordinary ignorance, or whether your system is genuinely braided with something else out of sight, entanglement. Start with the modest case. You prepare a particle by shuffling between several well-defined states according to some recipe you don't track in detail, maybe 70% one, 30% another, and you ask, what should I expect? The density matrix is the average ledger of those possibilities, and it predicts all observable statistics for any question you later ask. Different shuffles that yield the same ledger are operationally indistinguishable to you, which is the first lesson. A density matrix encodes everything that can be learned from this system alone, not a confession about how a lab technician rolled their dice. Now, for the deeper blur. Take a pair of systems and let them become entangled. Then close your eyes to one of them and look only at the other. The piece you keep no longer has a sharp, personal state because some of its potential is tied up in correlations with the partner you refuse to see. And the correct description is again a density matrix. But this time, the mixing is not about hidden labels you could recover by asking the right clerk. It is about relationships that live between parts. No amount of interrogation of the local piece can reveal which pure story the whole pair is telling, because the very question, which one, has no answer inside one subsystem alone. You can feel this difference with two analogies. Ignorance is a sealed envelope drawn from a known deck. You could, in principle, find the original card if the envelope were opened by the person who sealed it. Entanglement is two envelopes whose cards were printed on translucent paper so that the ink patterns cross-reference. Opening only one never reveals the full design, and the other envelope is not carrying a mere label, but half a motif. Practically, the same mathematics handles both because nature doesn't care why you lack information when it comes to predicting the next click. Locally, a mixture born of shuffling and a mixture born of entanglement can look identical, and this is where people sometimes get lost. The way out is operational. If your uncertainty is ignorance, there exists a hypothetical book listing which pure state you had each time. And if someone showed you the page, you could sort your data into uniform subsequences and see sharper patterns. If your uncertainty is entanglement, no such book exists inside your lab. The extra specification is woven into the absent partner, and only by regaining access to that partner, or by having engineered a good stand-in for it, can you unwind the blur. This brings you to a profound organizing idea called purification. Every mixed state you ever write can be viewed as part of a larger, perfectly pure state, with the missing clarity living in another system. It's not a loophole, it's a tool. By treating noise as coupling to an environment and your mixed state as a partial view, you get a recipe for building error correction, hide the fragile part in correlations you can later recover, for reversing certain kinds of apparent randomness, return the environment's record and coherence returns, and for seeing why some mixtures are stubbornly irreversible because the environment's record has flown off into countless, uncontrolled places. For a single, two-level system, you can visualize the story as a globe of possibilities. The pristine states live on the surface. As you average or entangle, your representative point moves inward. How far toward the center you've drifted is a measure of how diffuse your predictions have become. But don't be fooled. Two very different histories can land you at the same location inside, and the density matrix wisely refuses to promise more structure than your experiments can justify. This caution becomes a strength when you design measurements. The density matrix tells you exactly what any detector will see on average, and it lets you test for subtle quantum features even when you don't have a pure specimen. For instance, you can witness entanglement between two parts by checking whether the joint density matrix violates certain inequalities, or you can estimate resources like coherence, useful for interference, and magic, useful for quantum computation, by functions of the matrix that behave like honest meters, rising when you add the resource, falling under noise. In laboratories, the matrix is your workhorse. State tomography reconstructs it from many views so you can predict future outcomes. Process tomography and its modern, self-consistent cousin, gate-set tomography, tell you how matrices change under the actions your devices perform, noise channels that engineers talk about, dephasing that smears phases, amplitude damping that leaks energy, are nothing but rules for how these matrices evolve when your system brushes against a real environment. And temperature itself is encoded as a particular family of density matrices that weight energy levels according to a thermal recipe, which is why statistical mechanics and quantum theory meet so naturally in this formalism. The philosophical temptation is to ask whether a mixed state really is a lottery or really is a slice of a larger whole. The honest answer depends on access. If you can, in principle, bring back the partner and reverse the coupling that sent your clarity away, then treating the mixture as entanglement pays off. Quantum erasers, dynamical decoupling, and error correction all live here. If the partner is gone for good, scattered into air and table and time, then for you the mixture is effectively ignorance, and the right move is to model it as such, set error bars, and build robustness. Either way, the density matrix is the same object, and this unity is the point. It is a predictive summary of everything you can verify about your system given what you control. There are crisp, testable differences when you go beyond a single local view. Mixtures from ignorance cannot produce certain non-classical correlations, no matter how cleverly you process them, while mixtures from entanglement can, once the appropriate, partner is invited back to the stage. That is why protocols like entanglement swapping or teleportation are possible for one and impossible for the other. Locally, though, both mixtures give you identical yes-no odds for any question you pose, and the density matrix refuses to guess which cosmic story produced those odds. As you grow into this picture, a few habits of thought help. Stop asking for a narrative the data cannot support. Learn to read the eigenvalues and symmetry of a matrix as fingerprints of how many effective alternatives are still alive. And view increases in entropy not as moral decay, but as accounting for information that has slipped into places your instruments don't touch. The closing comfort is simple. By separating, I don't know which preparation we used, from this system, is knitted to something I don't see. Without conflating their predictions, density matrices give you a calm, operational realism. They let you build, compare, and improve devices in a world where isolation is a luxury and correlations are everywhere. And they teach a quiet life lesson along the way. Before you blame yourself for a blurry picture, ask if you're merely uninformed or if the subject is genuinely entangled with its surroundings. Either way, the cure is not wishful thinking, but better control, better context, and a model honest enough to tell you what can be sharpened and what must be accepted, for now as part of the fabric that binds things together. Operator algebras, the grammar of quantum talk. You learn any new language by listening for its grammar before you memorize its words. And in quantum theory, the grammar is not a list of particles or waves, but a web of actions you can take and how they compose. This is what operator algebras give you. A disciplined way to talk about every question you might ask of a system, how answers combine, which questions can be asked together, and how time, symmetry, and information weave through the whole conversation. Start with the gentle idea that an observable is just a controlled act. Shine this light, tune that frequency, read this meter, and to each act you attach a rule for producing numbers from states. Collect all such acts that your lab can perform and close them under the ways you naturally combine actions. First do A, then B. Add two readouts to form a new one. Take the mirror image action that undoes phases, and you get an algebra, a stable family of operations that captures the logic of your experiments. When every member of that family cooperates with every other, order never matters. You are in a classical world, because the algebra is commutative, and there exists a common picture in which all properties have sharp values at once. The moment order matters, you have stepped into the quantum. The algebra is non-commutative, and the grammar itself forbids certain sentences from being rewritten without changing their meaning. The power of this viewpoint is that it takes you out of the coordinates of a particular textbook and into a coordinate-free description. A state becomes nothing mystical, only a rule that assigns average outcomes to all the actions in the algebra, subject to the single honesty condition that obviously positive tests never return negative averages. You can think of it as a consistent betting book for your lab, and from that book, an abstract theorem, no need for symbols here, tells you how to build the usual Hilbert space and recover the familiar vectors and operators as a representation of your algebra. In that sense, the wave function stops being the sole protagonist and becomes a convenient dialect. The underlying grammar is the algebra itself, and you can switch dialects without changing the play. With this grammar, time becomes a structured edit. A dynamical law is an automorphism of the algebra, a way to push every permissible action forward consistently so that predictions march along in step. Thermal equilibrium is no longer a vague hand wave but a crisp condition that ties dynamical flow to a special state through a balance identity. So, being at a given temperature is a statement about how time-twisted actions look the same on average as their untwisted partners. Symmetries acquire the same clarity. A symmetry is an automorphism that leaves the state you care about unchanged. And if you want to see that symmetry on stage, you implement it with reversible transformations on your representation space. The upshot is that conservation laws and selection rules drop out of the algebra, the way grammar yields rules of agreement in a sentence, no extra metaphysics required. Subsystems, often a source of confusion, also become tidy in this frame. A part of a system is just a subalgebra, a subset of actions you decide to consider, and independence means two subalgebras commute. What you do on your bench cannot jostle what I can do on mine. Correlations then live as states on the larger algebra that fail to factor through the two parts, and entanglement stops being a spooky slogan and becomes the simple fact that some global states cannot be written as mixtures of local expectations. Even locality in field theory, so hard to visualize, is tersely expressed as an assignment of algebras to regions of space-time with the property that distant regions commute. This is quantum talk written as a city map, where each neighborhood has its own rulebook and overlapping neighborhoods must agree on the overlap. The classification of these algebras is not dry taxonomy, but a guide to what kinds of phenomena are possible. At one end, you have well-behaved type 1 algebras that match the intuition of finite systems and clean tensor products. Further along, you meet type 2, which capture the physics of infinite, homogeneous media where sizes can be compared as ratios without absolute counts. And at the frontier, you hit type 3, the natural habitat of local quantum fields where the very idea of carving a sharp subsystem into independent pieces breaks down and familiar entropies misbehave. This explains in structural terms why entanglement at short distances is so stubborn and why naively counting degrees of freedom fails in relativistic settings. Measurements and noise, the daily bread of a lab, fit the grammar just as snugly. A measuring device is an instrument, a map that takes your algebra of intended actions to a larger algebra that includes the readout. And the only physically sensible maps are those that send good bets to good bets, even when you imagine the device as part of a bigger setup. That is the content of complete positivity, and it is the algebraic way of saying your model will not predict nonsense when embedded in a more complicated experiment. Remarkably, every such honest map can be realized by temporarily enlarging your world, performing a reversible step, and then ignoring the ancilla. So every irreversible process is a reversible one with context forgotten, a moral that directly informs how you design sensors, memories, and error correction. From the same vantage, error-correcting codes are not magic incantations, but subalgebras that your noise maps leave undisturbed. Recovery is a map that restores the intended grammar on that subalgebra, and the conditions for correctability become transparent the moment you state them in the language of commutants and centers. What the noise respects, you can preserve. What it scrambles across the algebra, you must redesign or protect with redundancy. Even superselection rules that draw hard lines between sectors of a theory show up as elements in the center of an algebra, commuting with everything and forcing you to speak in separate chapters. A structural reason some superpositions are not merely unlikely, but meaningless in the intended grammar. If this sounds abstract, notice how the algebra quietly disciplines real design. When you lay out a quantum processor, you are choosing the algebra of controllable actions and the noise maps that chew on it. When you build a sensor, you are deciding which subalgebra of signals you can amplify without drowning others. When you simulate a material, you pick an algebra that encodes its locality and symmetries and evolve states within it. Done in this language, the difference between a toy model and an honest one is whether the grammar you chose can actually be implemented as compatible actions in hardware. There is also a conceptual dividend. The old rivalry between states evolve and observables evolve dissolves, because both are shadows of a deeper fact. The pairing of states with algebras is what carries predictions, and you are free to push the state forward, pull the algebra back, or do a bit of both, as long as the pairing remains consistent. Choose the picture that makes the bookkeeping lightest and the physics most transparent. Perhaps the most surprising gift of operator algebras is how they generate dynamics from stillness. Given only a state in its algebra, a deep theorem assigns a canonical one-parameter flow, the modular flow, that reveals which transformations are natural relative to that state. In high-energy theory, this abstract flow turns into concrete physics, linking horizons and heat, entanglement and motion, reminding you that time and temperature are not external dials but properties, emerging from the way a state sits inside its grammar. If you want a human-sized echo that stays faithful to the science, hold this. Grammar does not constrain thought to be dull, It makes thought legible and powerful. With a shared grammar, people can write poetry, prove theorems, or draft laws. With an operator algebra, you and nature share a grammar that lets you pose compatible questions, track symmetries, define parts, and recognize when a hoped-for action is simply not meaningful. You trade a little wildness for coherence and get in return a language in which design, prediction, and explanation line up. So when you next read a paper crowded with symbols, you can soften your gaze and ask the grammar questions instead. What is the algebra of acts? Which subalgebras mark the parts? How do time and symmetry move the sentences? Where does noise map the words, and what state is doing the reading? Answer those, and the blur of notation sharpens into a story you can follow. One in which the invisible scaffolding of operator algebras quietly holds the whole conversation together while you attend to the meaning. Renormalization. Intuition. Why scales matter. Take a map and try to measure a coastline with a ruler, then switch to a shorter ruler and watch the length grow as hidden bays and ragged inlets appear. Keep shrinking the ruler and the number climbs. Again, not because the land changed, but because your question did. The scale of your look rewrote the answer. And that is the doorway into renormalization. The disciplined realization that what you call a constant, a law, or a parameter is often a summary that depends on how closely you are looking, and that the right way to do physics is to track how those summaries change as you zoom. You already trust versions of this without naming them. A cup of coffee is simple at the table, smooth, brown, hot, but under a microscope it's a crowd of jittering molecules. Step back further and it becomes a moving patch of fluid with eddies and convection cells. No single description is a lie, but each one has its own variables and its own numbers that matter at that level. Renormalization takes that everyday wisdom and turns it into a calculus. Start with a detailed model. Soften your gaze by coarse-graining tiny wiggles you can't or won't follow, and watch what happens to the surviving parameters as you flow from small scales to large. In magnets, this looks like Kadanoff's block spin picture. Gather a small cluster of microscopic spins into a single block spin. Ask how blocks talk to blocks, and then repeat. Certain couplings grow as you zoom out. They are relevant, shaping the large-scale behavior, while others fade, irrelevant, their detailed values washed away. At a critical point, where a magnet is on the knife edge between ordered and disordered, the flow stalls at a fixed point, and the system forgets its microscopic details so thoroughly that iron and liquid helium share the same exponents. That surprising sameness is universality, and it is why nature sometimes looks simpler when it is wild. In quantum fields, the script rhymes. A charged particle is surrounded by a cloud of virtual excitations that screen it, so the effective charge you infer depends on how closely you probe. At long distances, the cloud is bulky and reduces what you feel. At short distances, you push through the cloud and the bare interaction strengthens. The language we use for this is running couplings, and the speed and direction of their change is set by a flow equation, the beta function, that encodes how integrating out finer ripples reshapes the rules at your current scale. In quantum chromodynamics, the running is dramatic in the opposite direction. Quarks are freer at short distances and more tightly bound at long ones, a phenomenon called asymptotic freedom that explains why high-energy scattering sees quarks behave almost like independent bullets, while low-energy physics traps them in protons and neutrons. If the word divergence has ever bothered you in field theory, renormalization is the cure, not because it sweeps infinities under a rug, but because it insists you were asking for the wrong thing. You don't measure a bare mass or a bare charge in isolation. You measure the response of your apparatus at a given resolution, and you define your parameters by those responses. Shift your resolution and the fitted numbers shift with it in a calculable way. Once you accept that questions and scales come as a pair, the apparent infinities turn into a bookkeeping reminder to always specify a cutoff and a renormalization condition before comparing theory with experiment. The core mechanism behind the scenes is wonderfully visual. Imagine your system's possible interactions as arrows in a high-dimensional space. Coarse graining is a gentle push in that space, and the arrows bend as you lower your resolution. Flows that head toward the same destination explain why wildly different microscopic models can land in the same macroscopic class. Flows that run away warn you that certain features, like a fine-tuned balance, will be unstable unless you protect them by symmetry or design. Along the way, you learn the taxonomy of relevant, irrelevant, and marginal directions, and the intuition that a good effective theory keeps only the few arrows that matter at your scale and discards the rest without guilt. This is not only philosophy, it is engineering in condensed matter labs and particle colliders alike. When materials scientists predict how a thin film will switch from insulating to conducting as impurities change, they are reading a flow near a fixed point. When high-energy physicists extrapolate cross-sections from one collider energy to another, they are evolving couplings with the scale. When a chemist uses a dielectric constant to summarize a solvent's effect rather than modeling every molecule, they are integrating out fast degrees of freedom and keeping their impact in a renormalized parameter. When a quantum engineer models a qubit's environment as a spectral function that is flat or colored depending on frequency, they are deciding which fluctuations at which scales dominate the noise and therefore which controls will matter. Even the way you simulate systems mirrors this logic. On a lattice, you can coarse-grain blocks to accelerate computation, adjusting interactions to keep predictions fixed. In tensor networks, you compress information by keeping only the most relevant correlations, a practical echo of irrelevant directions fading. In data science, you regularize models to prevent small-scale noise from masquerading as signal, a renaming of the lesson that not every fine detail deserves a parameter. The naturalness, debates you may have heard about, why some numbers in nature are small without apparent symmetry, why some masses sit so far below the higher scales, are renormalization questions too. If flows tend to drag parameters towards certain values unless protected, a tiny unprotected number looks like a suspicious fine-tuning. The proposed cures, new symmetries, dynamics that pin flows to special lines, or the acceptance that our effective description lives in a pocket of a larger landscape, are different ways of addressing how scales talk to one another. There is also a gentle but important moral about honesty in modeling. Don't ask a theory to predict beyond its resolution without admitting an error bar that grows with the extrapolation. An effective theory is not a compromise. It is a promise tailored to a scale, and the promise is strong because it refuses to pretend. If tomorrow you gain access to shorter distances, you can revise the theory by letting new terms appear in the grammar and by recalibrating parameters so that old successes remain intact at the old scales. Continuity is the gift of the flow. If you need a more tactile anchor, think of a sound equalization. A song can be bright or bass-heavy depending on how you set the sliders. The identity of the song remains, but different ranges dominate. Renormalization is the universe's equalizer for interactions. Turn the scale knob and the mix of contributions shifts, while the overall piece keeps making sense. Fixed points are the presets that return again and again, no matter where you start, and relevant sliders are the ones your ear still notices after you change the volume. And because you live in a world with many scales, from the flicker of a neuron to the swirl of a hurricane, this way of thinking spills outside physics, into reasoning itself. Define the resolution of your question. Keep only the variables that stay audible at that resolution, and let go of the rest. If a pattern survives as you zoom and a few parameters govern how it changes, you've found a renormalization structure and a route to prediction. The closing comfort is that renormalization does not cheapen laws by making them context-bound. It dignifies them by explaining why they work so reliably where they do, and how to translate them when you change your lens. It replaces the fantasy of one perfect description for all scales with a more generous promise. For each scale, there is a near minimal description with only the knobs that matter, and the relationships between these descriptions can be charted. Learn to move along that chart, and the world's complexity becomes navigable. Coastlines that once looked pathological become measurable. Materials that once seemed capricious become classifiable, and forces that once appeared to be different faces of chaos resolve into a changing yet intelligible grammar of scale. Quantum reference frames. Facts shift with perspective. Begin with a small rebellion against habit. You have always told the truth of a scene by anchoring it to a sturdy bench, the lab table, the floor, the rest frame of common sense. But what if the bench itself could wobble, drift, even live in a superposition of positions? Quantum reference frames take that what if seriously and show that many facts you treat as absolute, where something is, whether two systems are entangled, even which clock is really ticking, become relational statements that can change cleanly and lawfully when you describe the world from the point of view of a different, fully quantum bench. In everyday physics, changing frames is a matter of translation and boost. You subtract a velocity, add a phase for convenience, and the equations keep their form. In quantum mechanics, the frame can be an actual object with finite mass, uncertain orientation, and dynamics of its own. So the transformation from one perspective to another is not a semantic relabeling, but a concrete operation that re-expresses all degrees of freedom in relative terms to the chosen system and pays for that choice with entanglement and uncertainty where appropriate. Picture two cold atoms in a trap. From the external laboratory's coordinates, the pair might be in a fuzzy, correlated state, neither sharply here nor there. But if you switch to the atom A frame, recasting all positions as where is B relative to A, you can find a description in which B sits in a narrow packet, while the trap and lab walls take on the fuzz that A used to carry. The physics has not changed. The probabilities you can check remain consistent, but the facts you emphasize have rotated. Delocalization that looked like a property of a particle now shows up as a property of the lab measured from the particle's point of view. This perspective swap is not wordplay. It is implemented by a precise change of variables that trades global coordinates for center of mass and relative ones, and then declares one subsystem the reference, conditioning everything else upon it. Because the reference has finite precision, any frame you build from it inherits limits. A light gyroscope used to define up can itself precess and spread, so angles learned relative to it carry quantum noise. A small clock used to define now has phase diffusion, so time learned from it acquires a blur. The echo of this is practical. Metrology limits for rotation, phase, and time are not only about your probe, they are about the quantum quality of your frame. The idea takes on richer shades when you move from space to time. In a relational view, evolution can be understood as correlations between a system and a clock that share a joint state. Fix the clock to one reading and the rest of the world looks as if it has advanced. Condition on a different reading and you rewrite the same correlations as a different slice of history. Adopt the clock's perspective and you recover familiar dynamics. Adopt a spectator's perspective with no privileged clock and you describe a timeless joint structure whose temporal flow appears only when a frame is chosen. Time, in this telling, is not a universal river, but a family of readings tied to physical clocks that never tick with infinite sharpness. Gravity makes the lesson concrete without mysticism. Lift a quantum clock to a higher shelf, and its tick rate shifts by a tiny but measurable amount. Put the clock into a spatial superposition across heights, and the relative tick between the two paths can dephase other systems coupled to it. From the clock's own frame, it ticks steadily while the rest of the world adjusts. From a distant lab's frame, the clock's uncertainty in position becomes an uncertainty in rate, and which time is right dissolves into which frame have you chosen to do the bookkeeping. Even statements about correlations depend on who holds the ledger. Two qubits that the lab calls entangled can, when described relative to one of them taken as a reference, appear locally pure with the rest of the universe carrying the burden of correlation. Conversely, a state that looked classically mixed from a crude lab frame can reveal crisp relational order once you hitch your coordinates to a smart, quantum-sharp reference. This is not permission for contradiction. It is a refinement of consistency. Different observers, especially those whose frames are quantum systems of finite size, will agree on all operationally comparable questions once their data are translated into the same frame, but they may package the same joint statistics into different narratives about where and when, because the transformations that connect their descriptions entangle and unentangle degrees of freedom in ways impossible for classical frames. The payoffs are immediate for design. Navigation on the nanoscale becomes a choreography of relational measurements. Set a molecule as the origin and read forces relative to it, rather than chasing absolute positions you cannot stably define. Distributed quantum sensors can treat one node's phase as the phase reference and rotate all others into its frame, gaining immunity to common mode noise that would have ruined an absolute scheme. Quantum networks can align their internal axes by exchanging small packets of entanglement that serve as seeds for shared frames, after which tasks like teleportation or clock synchronization run with fewer assumptions. There is also a resource logic humming under the hood. A good reference frame is a consumable commodity. Use it to define phases or angles too many times, and its own quantum state degrades, spreading the very orientation or timing you wished to keep sharp. Conversely, sharing high-quality references can lift otherwise forbidden tasks, letting you access relative phases or orientations that were formerly super-selected away. But unlike older stories that treated such rules as categorical, the quantum frame view makes them conditional. With the right shared reference, the prohibited becomes possible, and the degree of possibility is quantified by how much frameness you can afford to spend. Subtle experiments already exploit the theme. Interferometers that place not only particles, but also their beam splitters or mirrors into superposed motions reveal that interference visibility depends on whether you describe the setup from the lab's heavy frame or from the lighter device's own frame. Optomechanical platforms where a cantilever acts as both sensor and reference show that backaction and readout noise can be traded by redefining which subsystem plays the ruler, a choice that changes which correlations count as signal and which as disturbance. What should you carry away as a working principle? First, never speak of position, phase, or time without naming, even implicitly, the physical object that grounds your words. Second, expect that changing that object, adopting a new quantum reference, can move properties between system and context without altering any measurable prediction. Third, design protocols that treat frames as part of the hardware, with budgets, noise, and refresh cycles just like any other component. And there is a human echo to end on that does not cheapen the science. Many arguments in life pretend to be about facts in the void, when they are really about perspectives anchored to different frames, histories, aims, tools, each with finite resolution and noise. Quantum reference frames remind you to name the anchor, to admit its limits, and to learn the translations that carry meaning from one anchor to another. Do that, and apparent paradoxes soften into compatible accounts, and the world, physical and personal, stops demanding a single, absolute bench before it will let you tell the truth. Charge, parity, and time reversal symmetry. Stand in front of a mirror with a ticking metronome in your hand, and imagine three playful gods standing behind you, each with a single trick. One swaps every particle for its antiparticle, so charges reverse, but masses stay the same. One flips left and right, so your reflection's handedness is exchanged. One reaches for the time slider and runs the scene backward, so the metronome's click seems to march toward the past. The surprising story of modern physics is that each trick, taken alone, can fool nature only sometimes. But when the three are performed together, charge conjugation, parity flip, and time reversal, nature's deepest equations almost always shrug and say, "That's still me." A principle compressed into the phrase CPT symmetry, which tells you that if you rewind the world while looking in a mirror and exchanging matter with antimatter, the allowed processes line up again as if nothing scandalous had happened. To feel why this is both subtle and powerful, start with the mirror. For a long time, scientists assumed the universe had no preference for left or right, that a pinwheel of radioactive decay would spin the same way in your room and in its reflection. Then, in 1956, an elegant cobalt experiment showed that the weak force cares about handedness. More electrons fly one way than the mirror way, so parity can fail spectacularly. Charge conjugation fares no better on its own. Swapping particles with antiparticles does not restore the missing symmetry in those decays, but combine charge swap with the mirror, and many weak processes do regain balance. CP looks sturdier until you examine particles like neutral kaons or B mesons and find small, precise mismatches, tiny asymmetries in how matter and antimatter versions transform into each other that cannot be erased by a mirror. That discovery, first with kaons in the 1960s and later with B mesons, is not a footnote, but a structural twist in reality. It means the laws that govern micro-events draw faint but real arrows distinguishing matter from antimatter. Time reversal is trickier to picture because it is not only rewinding a film. You must also reverse motions in a way that keeps the dynamical rules intact, and while frictionless billiards reversed exactly retrace their paths, quantum processes with phases and interference complicate the intuition. Yet there are clever ways to catch time's mischief directly. Certain rare transitions among B meson states show a clear imbalance when you swap before and after a genuine violation of time symmetry that is consistent with the earlier CP imbalance once you accept the overarching CPT alignment. Why care about such bookkeeping? Because the three letters chain together consistency conditions that reach into almost every corner of high-energy and low-energy physics. CPT symmetry implies that a particle and its antiparticle have exactly the same mass and lifetime, that their gyromagnetic ratios are equal and opposite, that their spectral lines would match if you could build atoms from antimatter and check. We have tested these claims with obsessive care, comparing cyclotron frequencies of protons and antiprotons, measuring the magnetic moment of electrons and positrons to astonishing precision, building antihydrogen and reading its light. And, so far the numbers fall into line, which means the familiar framework we use to model fields and interactions retains its crown. A clean CPT violation would be a fire alarm telling you that one of the pillars, locality, stable causality, or the geometric rules of spacetime must be rethought. CP violation, for its part, carries cosmic weight. The visible universe is made of matter rather than equal parts matter and antimatter, a fact that demands three ingredients if you trace it to the young cosmos. Reactions that treat matter and antimatter differently, that's CP violation. Processes that leave overall charges rebalanced, and moments when the universe is far from equilibrium. The small CP effects we have catalogued in quark decays are not obviously large enough to explain the whole excess, which is why you often hear about searches for new sources of CP violation in the neutrino sector or in undiscovered particles. Here, precision becomes philosophy made tangible. A non-zero permanent electric dipole moment of a neutron, an electron, or a neutral atom would be an unmistakable sign of T and CP violation, even in quiet matter. So teams build exquisitely calm experiments in frozen gases, trapped ions, and ultra-cold neutrons to look for that tiny tilt, finding none so far, which tightens the leash on speculative ideas. Time's role appears again in gravity's presence. A clock raised in a gravitational field ticks at a different rate, and if you could place such a clock into a quantum superposition of heights, the relative ticking becomes a laboratory for how time and quantum phases mingle. From one reference frame, the clock runs steady and the world adapts. From another, the clock's own fuzziness appears as dephasing, but the combined CPT story survives these contortions. If you mirror and swap and rewind, the relational predictions return to form. This steadiness matters because it ties our basic symmetry claims to the geometry of spacetime rather than to a particular coordinate trick. The pragmatic payoff of mastering this grammar is that it tells you where to focus ingenuity. If you want to expose new physics, Do not look for gross violations of energy conservation or charge conservation in familiar regimes. Look where the symmetries are known to wobble. Build machines that monitor rare transitions whose mirror plus swap partners should be equal but are not. Hunt for long-lived particles whose decays trace a preference in the angle between decay planes. Compare spectral lines of antimatter and matter to more decimal places. Monitor neutral meson oscillations over large baselines to catch whispers of new phases. And push on permanent dipole moments, knowing that any sample above zero would be a headline that rewrites textbooks. At the same time, let CPT's resilience keep you humble. When disparate experiments agree to absurd precision that matter and antimatter share properties, you are being told that your basic theory, fields living on a smooth spacetime with local interactions, has not yet reached its limit in the regimes you can probe. The art is to test both the fragile and the robust at once, to look where cracks have previously formed, parity and CP, and to keep measuring the places that have not yet cracked, CPT. If you need a picture to carry, think of a dancer reflected in a floor-to-ceiling mirror while a camera rolls. Flip the costume from red to blue, swap left and right in the mirror, and run the recording backward. If the choreography, lighting, and physics are truly symmetric under those combined changes, the performance remains believable. Now and then, you notice a detail, a shoulder that favors one turn, a hem that catches light differently, that spoils one of the simpler flips. That is parity or CP failing. But were the entire trio of changes to ruin the piece, you would suspect the stage itself had shifted. CPT would be gone, and with it, the assumptions that keep cause and effect, locality and identity, legible. The quiet conclusion, then, is both technical and human. The universe makes room for asymmetry where it matters, seeding a cosmos that didn't annihilate itself into light, yet it preserves a deeper balance that lets you reverse, mirror, and swap your stories without breaking their core truth. Understanding which differences are allowed and which identities must hold is part of growing fluent in nature's language, and it leaves you with a calm respect for rules that are strong enough to guide and nuanced enough to let something interesting, like a world with more matter than antimatter and a time that seems to move forward, actually happen. No broadcasting. Why quantum data resists duplication. Picture a library that refuses to let you photocopy certain pages, not because of policy, but because the ink itself will not transfer cleanly. Every attempt to duplicate ends up smearing letters into new, unfaithful words, while oddly, some pages, those written in a very plain font, copy just fine. That is how quantum data behaves under no broadcasting. The rule that says you cannot take an unknown quantum state and distribute faithful copies of its informational content to multiple places at once unless that content is, in a precise sense, already classical. To understand why this is more than a fancier no-cloning, start by separating three jobs you often conflate: copying a record you've already extracted, copying a known template, and copying an unknown state. If you measure a qubit in a chosen basis and write down the result, the bit in your notebook is ordinary and can be duplicated without limit. That's record copying. If you are asked to fabricate many instances of a known state, you can prepare as many as you like. That's template copying. What fails is the dream of taking a single, fresh, unknown specimen and fanning out its full predictive power to several recipients in one operation so that each recipient can use their copy as if it were the original. The only time this succeeds is when the relevant states all commute, when there exists a single measurement that reveals the needed information without trade-offs, because then the quantum page is effectively written in that plain font, and the copy machine can read and replicate it without scrambling other letters. In every other case, the very features that would need to be preserved across copies are tied to questions that cannot be asked simultaneously with perfect sharpness. So any machine that tries to broadcast them must first choose a viewpoint, and that choice inevitably erases or distorts the parts that do not fit the chosen lens. The distinction between cloning and broadcasting matters because real data is often noisy or deliberately mixed. A laboratory source might emit a family of possible states with some randomness, and what users want is not a carbon copy of one pure draw, but a distribution-preserving replica that two or more parties can each hold. The no broadcasting theorem says, even this gentler ambition fails in general. Unless the family of states share a common set of classical features, you cannot build a device that hands each party a faithful marginal that carries the same predictive content as the input. In practice, that draws a bright line for network design. You can freely fan out classical labels stamped onto quantum carriers, like which of several orthogonal code words was used. But you cannot fan out the full richness of a superposition or the delicate relative phases that give quantum states their power. Engineers feel this when they try to design a quantum analog of a classical fan-out gate. You can copy a computational basis bit with a controlled knot, but you cannot make a general copy-everything gate without injecting noise that depends on the very thing you hope to preserve. Attempts to cheat with universal cloners buy reach at a price. They output approximate copies whose quality drops as you add recipients, and crucially the noise is structured in a way that reduces exactly the non-classical correlations you would have needed for later quantum tasks. These machines are not loopholes. They are reminders that in the quantum regime, duplication and disturbance are the same act wearing different hats. Broadcasting also fails for correlations in a way that teaches you what is truly quantum about joint systems. Suppose two labs share data in a state that has no entanglement, but still carries subtle, direction-dependent ties, what researchers call discord. If those ties are genuinely quantum, no set of local operations and helper ancillas can create two new pairs of labs that both share the original pattern of correlations with the original strength. Only when the shared state is fully classical on at least one side, meaning its statistics can be explained by a single, sharp local questionnaire, can you locally broadcast those correlations to many partners without loss. This no local broadcasting result is not a curiosity. It explains why certain distributed protocols demand fresh entanglement rather than cached side information, and why some datasets resist duplication even when every party promises to touch only their own hardware. It also underwrites security. Eavesdroppers cannot silently split a quantum transmission into two equally useful feeds. If they siphon off enough to learn, they degrade what remains, and that damage can be detected. Quantum money and unclonable tokens take this to the bank, literally, by encoding value in states that any counterfeiter must either measure and thus disturb, or try to clone and thus reveal imperfections, while legitimate verifiers, armed with the right tests, can tell the difference. The theorem reaches into mundane lab routines too. Consider a calibration file for a sensor. In the classical world, you send identical copies of the file to every node, and you're done. In the quantum world, the file might be an ensemble of states that tune a device when fed through it, and your instinct to distribute those states intact will fail unless you redesign the protocol to move descriptions rather than raw quantum samples, or to use teleportation-style relays that never attempt duplication, but instead reconstitute the state at its destination after a one-time joint operation and a classical message. That is why quantum repeaters, the backbone of long-distance quantum networks, do not copy traveling qubits the way classical repeaters copy bits. They stitch distant links together by generating entanglement over short spans and then swapping it stepwise, a choreography that preserves non-classical correlations without ever making extra instances. Likewise, error correction does not contradict no broadcasting. A code spreads the information of one logical qubit across many physical carriers in such a way that no proper subset contains the whole. The redundancy is in correlations, not in copies, so no single share lets you counterfeit the original, yet the right collective recovery undoes typical noise. This is the subtle art no broadcasting forces you to learn. Move value into patterns rather than into clones. Once you see the shape of the rule, many confusions quiet down. When someone says, "We copied a quantum image," ask whether they measured it into a classical record first. If yes, they copied a record, not the underlying state. When a proposal promises secure multicast of arbitrary states, look for either a commuting ensemble, which makes the states effectively classical, or a hidden central operation, which means they are not broadcasting at all, but redistributing with one-time joints. When a business pitch claims back up your qubits in the cloud, ask whether they mean tomography, learning a description you can later re-prepare, error correction, spreading information across nodes so that losses can be healed, or snapshotting a classical transcript of control pulses. Any promise of literal duplication of unknown states should be met with the same skepticism you reserve for perpetual motion. Counterintuitively, no broadcasting also enables possibilities by forcing architecture to be honest. Because you cannot duplicate. You are pushed toward designs that are composable. Prepare once resources shared across teams. Entanglement that is consumed like fuel. And workflows that convert fragile quantum features into robust classical outcomes at the last responsible moment. This shift yields cleaner accounting. What was spent, what was preserved, what became classical and thus copyable. And it aligns with thermodynamic prudence. Each conversion from quantum to classical comes with a footprint you can quantify and manage. The rule even offers a soft lesson about creativity and control. You cannot have the whole of a living, coherent pattern in many places at once. When you try, you either reduce it to a summary anybody can circulate, or you accept that its power lives in ties that must be built fresh where they are needed and will be spent when used. The closing clarity is simple, and it will guide you whether you're designing a protocol or just making sense of claims. Quantum data resists duplication. Not because the universe is stingy, but because the most useful features of that data are defined relationally. They depend on questions that cannot be answered all at once without damage. Whenever your task can be rephrased as copying answers to a single compatible question, you can broadcast with abandon. Whenever it requires preserving incompatible possibilities, in parallel, the copier becomes a grinder, and what comes out are fragments with less future in them than the original had. Learn to spot which kind of information you're holding, and you'll stop fighting the rule and start building with it. Routing classical summaries where copies are fine, cultivating entanglement where uniqueness is strength, and using the world's own resistance to duplication as both a shield against theft and a compass for honest design. Resource theories, quantifying the strange. Start with a simple promise we rarely keep. If something is valuable, measure it, price it, and track how it moves. Resource theories take that promise into the quantum world and turn strangeness into a budget by declaring, with great sobriety, what you are allowed to do for free, which objects count as ordinary, and which shards of the unusual must be spent to achieve feats no ordinary toolbox can manage, so that entanglement, coherence, magic, asymmetry, and even thermodynamic usefulness stop being misty virtues and become currencies you can earn, convert, and burn under rules as clear as a ledger. The structure always begins the same way. Pick a background that represents your practical limits, say, operations you can implement easily, or states you can prepare without cost, and call those free. Everything they can generate without extra help is also free. Now pick a phenomenon you care about. Long-distance correlations, phase-sensitive superpositions, non-classical logic for computation, bias away from thermal equilibrium, and call states that lack it free states. Any state that has the phenomenon becomes a resource, and any operation that would create or increase that phenomenon for free is forbidden unless you pay. From there, two big questions organize the subject. How can one resource be transformed into another using only free moves, and how do we assign numbers, monotones, that never increase under free moves so we can compare, price, and plan across many steps? At human scale, this is no different from budgeting time or energy. You can walk, but you cannot teleport. You can rearrange furniture, but you cannot conjure a grand piano. Resource theories simply translate that sobriety to lab constraints. With local control, you may swap qubits and measure them. Yet you cannot summon entanglement in the absence of a quantum link. With phase-blind tools, you may shuffle populations, yet you cannot mint coherence. With thermal reservoirs and energy-conserving controls, you may shuffle heat, yet you cannot extract work from a system at its own temperature unless you bring in athermality from elsewhere. Once the free restricted line is drawn, remarkable regularities appear. In the many-copy limit, interconversion rates often stabilize into exchange laws. So many units of resource A reliably turn into so many units of resource B per copy, while in the single-shot regime, you meet finer-grained second laws that cap what is possible on a one-off basis and reveal that certainty is expensive and slack is power. In between, catalytic effects appear, where a helper state that you promise to return unchanged can open pathways that are otherwise closed, the way a measuring cup lets you bake a cake without being eaten itself. Sometimes even embezzling, helpers exist whose tiny distributed changes can fuel a sequence of nearly free upgrades, teaching you to be explicit about what unchanged must mean in contracts you plan to honor. Practical wins flow from this bookkeeping because fuzzily admired qualities become engineering targets. Want long-distance teleportation? Then entanglement is your currency, and distillation protocols are refineries that turn many noisy bonds into a smaller stack of high-grade ones with clear exchange rates and loss accounting. Want quantum speed-ups in algorithms that resist classical simulation? Then magic, the non-stabilizer component of your states, is the fuel and magic state. Distillation tells you how many high-octane catalysts you must invest per target gate. Want sensors that beat classical limits? Then coherence and asymmetry, relative to the signal's symmetry group, are your coins, and you design probes and controls that spend those coins exactly where sensitivity grows fastest, rather than letting them leak into irrelevant channels. Want to harvest work from information? Then thermal populations are your stash, and the thermodynamic resource theory quantifies how much ordered energy you can pull out if you are honest about fluctuations, catalysts, and the price of certainty. The discipline also clarifies disappointments before you waste money on them. No broadcasting, seen through this lens, is the statement that the copying you want would increase certain monotones for two parties at once, using only local, free moves, disallowed by design, so you stop chasing an impossible fan-out and build repeaters that swap entanglement instead. Similarly, the dream of error correction without overhead becomes a question about whether your noise map preserves a protected subalgebra for free. If not, the theory tells you what redundancy and what auxiliary resources your recovery must consume. Importantly, you do not need equations to feel the moral weight. A good monotone is nothing but a trustworthy meter, relative entropy of a property, geometric distance from the free set, robustness against dilution, that never rises when you refuse to pay. A conversion protocol is a recipe that spends 1 meter to raise another, and a no-go theorem is a sign on a locked door that saves you time by making the cost of breaking in explicit. The framework even reconciles tidy asymptotic laws with messy, real experiments. In the infinite copy dreamland, irreversibility often fades. What you can distill, you can dilute back with fair exchange. Yet on the single device bench, you pay penalties that show up as additional inequalities. Resource theories record both stories so you can scale expectations. Lab teams know how good could be and how far their current single-shot routines are from that bound. When different kinds of strangeness meet, the ledger keeps them honest by exposing conversion rates. Coherence can be cashed out into entanglement by sending a coherent system through a beam splitter with vacuum, but not at one-to-one generosity. Asymmetry can be traded for precise timekeeping, but the price grows with desired stability. Thermodynamic athermality can cede coherence if and only if you allow phase-sensitive controls. Otherwise, the exchange rate is zero. These rates are not prejudices, but the best deals the universe offers under the rules you accepted at the start. And if the word price worries you, notice the ethical turn it brings. When a paper claims a protocol, creates a resource. With trivial means, the framework hands you the cross-examination sheet. What did they call free? Which monotone went up? Where did the hidden fuel enter? And empty claims evaporate. When a proposal is sound, the same sheet becomes a blueprint. Here is the refinery. Here the waste heat. Here the catalyst to reclaim. Here the bound that proves why more is impossible. The quiet philosophical gift is that resource theories make peace between wonder and work. They let you keep the sense that entanglement, coherence, magic, asymmetry, and athemality are strange, while also giving you rulers that make the strange actionable. They teach you to ask before a feat dazzles or disappoints, which background you are willing to count as free, which currencies matter in that background, and whether your plan respects the monotones that guard the vault. And they end with a humane reminder: parts of life, like parts of physics, thrive under budgets. Not because scarcity is a virtue, but because clarity is. When you name what costs and measure what grows, you stop chasing fantasies and start building engines that do what you intend, spending strangeness where it buys meaning and saving it where it would only glitter.